The question, "Are we alone?" has quietly guided some of NASA's most ambitious missions. Every rover sent to Mars, every telescope peering into the deep dark, carries a piece of that ancient curiosity. But the search for life is not as simple as pointing a camera at the stars. Inside NASA, the hunt for alien life is both scientific and deeply human. It's shaped by politics, budget meetings, and public expectations, but also by wonder, imagination, and patience. The people leading this search know that a discovery may come tomorrow, or never at all, yet they keep looking because finding life beyond Earth would change everything we know about who we are and where we come from. This is the story of that search, the quiet, determined effort to find company in the vastness of the universe. The question that drives NASA: are we alone in the universe? This question is the reason humans first pointed radio antennas toward the stars, the reason we study the chemical makeup of distant atmospheres, and the reason we send small machines to wander across cold, dusty planets. NASA may be an organization built on technology and science, but beneath all the machinery lies something deeply human, a search for connection, for understanding, for a sense of place in the vastness of the cosmos. When NASA was founded in 1958, the world was gripped by a mix of fear and wonder. The space race had begun, and exploration beyond Earth had become not just a matter of curiosity, but of national pride and survival. Yet even amid the political pressures of the Cold War, many of the early NASA scientists saw something much larger in their work. They were not only building rockets to beat an opponent, they were opening a new frontier for all humankind. Every spacecraft, from Mercury to Apollo, carried a quiet hope that somewhere out there, beyond the blue sky, other beings might also be looking up and wondering if they were alone. The first step was to look back at Earth itself. From orbit, astronauts saw the world as a single fragile sphere, alive in a way that no other place seemed to be. The famous Earthrise photograph taken by Apollo 8 in 1968 captured not just the beauty of our planet, but its uniqueness. Surrounded by the empty darkness of space, Earth glowed with color and motion. It was a living world among lifeless ones. If life could thrive here, under the right conditions, could it not arise elsewhere too? This question began to shape the direction of NASA's missions. It was no longer enough to explore space for the sake of exploration. The focus shifted toward finding clues about life, how it begins, how it survives, and where it might exist beyond our planet. The search for life became the thread connecting everything NASA touched, from the study of distant galaxies to the analysis of tiny Martian rocks. Even the design of spacecraft changed, evolving from tools of exploration into instruments of discovery, equipped to detect the faintest chemical whispers that might point to biology. The robotic explorers sent to Mars were built with this mission in mind. When the Viking landers touched down on the Red Planet in 1976, they carried some of the first experiments designed to test for life beyond Earth. NASA was no longer just mapping the planets. It was searching for signs of something that could speak to our deepest question. Every decade since, NASA's methods have grown more refined. The agency learned to look for life not just in the form of organisms, but through the traces it might leave behind: water, carbon compounds, methane, and oxygen in alien skies. Missions like Kepler and TESS began scanning thousands of stars for planets like Earth, worlds that might sit at just the right distance from their suns for liquid water to exist. The discovery of thousands of exoplanets transformed our understanding of how common planets are. Suddenly, the universe seemed full of potential homes for life. The question no longer felt like a distant dream. It became a scientific investigation with real data, real possibilities. But behind all the data and hardware, the question remained personal. To find life elsewhere would be to find a mirror, a reflection of ourselves in the universe. It would show that life is not an accident of Earth, but a pattern written into the fabric of reality. And if life is common, then intelligence, minds capable of curiosity, of wonder, of asking their own questions, might also be out there. The possibility reshapes how we think about everything. our origins, our purpose, our place in the grand design of nature. Even when the missions have nothing to do with life directly, the question still echoes in the background. When the Voyager spacecraft left the solar system, it carried the golden record, a message from Earth to whoever might one day find it. It was a gesture of hope, an invitation to the unknown. The record contained images, sounds, and greetings from our world, as if NASA knew that one day, somewhere far away, someone might be listening. Voyager's journey became a symbol of humanity, reaching out into the dark. NASA's telescopes have also become part of this ongoing conversation. The Hubble Space Telescope revealed the sheer scale of the universe, billions of galaxies, each with billions of stars. Then came the James Webb Space Telescope, designed to peer even deeper, to look at the light from the first galaxies and the atmospheres of distant worlds. Each observation brings us a little closer to understanding how common life might be. Webb's instruments are sensitive enough to detect chemical fingerprints, gases like methane or ozone that on Earth are linked to living processes. With every new discovery, we move one step closer to an answer, even if that answer remains out of reach. Every time a rover drills into Martian rock, every time a telescope stares at a faraway planet, we are not only gathering data, we are seeking connection. The universe is vast beyond comprehension, but in asking this question, NASA reminds us that we are not just observers of it. We are participants. Our desire to know if others exist out there is, in a way, an expression of our own need to belong, to know that we are part of something larger than ourselves. The legacy of Viking, the first search for Martian life. In the mid-1970s, when NASA's Viking program was launched, it carried one of the most daring goals in the history of science: to search for life on another planet. Never before had humanity tried to look directly for living organisms beyond Earth. For all of our telescopes and spacecraft, Mars remained a mystery, a reddish blur in the night sky that had long inspired stories about canals, civilizations, and lost Martians. Now, for the first time, NASA had built machines that could actually land there and test the soil itself. The Viking landers were not just missions of exploration. They were humanity's first scientific handshake with another world. Viking consisted of two identical spacecraft, Viking 1 and Viking 2, each made up of an orbiter and a lander. The orbiters would map the Martian surface, while the landers would descend to conduct experiments right on the ground. Launched in 1975, they arrived the following year, Viking 1 touching down in Christ Planitia in July 1976, and Viking 2 landing in Utopia Planitia in September. For the first time, high-quality images of the Martian landscape began streaming back to Earth. A world of orange deserts, scattered rocks, and endless horizons beneath a pinkish sky. The images were stunning, but the true excitement lay inside the landers themselves, in the small boxes of instruments. The Viking biology experiments were built around three key tests. Each was designed to look for subtle signs of biological activity, changes in chemistry that might reveal the presence of living microbes hidden in the Martian soil. The experiments were ambitious, intricate, and years ahead of their time. They were designed under the assumption that if life existed on Mars, it might be something like microbial life on Earth, feeding on nutrients and releasing gases as a byproduct. The scientists hoped that by feeding the soil small samples of nutrients, they could detect such reactions. The first test was called the Labeled Release Experiment. It was designed by biologist Gilbert Levin, who believed that even the smallest trace of microbial metabolism could be detected if the right nutrients were used. In this experiment, the Viking landers added a drop of nutrient solution to a small scoop of Martian soil. The nutrients contained carbon atoms labeled with a radioactive isotope. If microbes were present and metabolized the nutrients, they would release radioactive carbon dioxide gas, which the lander could detect. To everyone's surprise, when the experiment was run, the instruments showed an immediate reaction. The data suggested that something in the soil was indeed producing gas, just as living microbes would. The second test, called pyrolytic release, was designed to see if any organisms could take in carbon from the atmosphere and convert it into organic material, much like photosynthetic bacteria on Earth. The Viking lander exposed Martian soil to a mixture of gases similar to Mars's thin atmosphere, which included radioactive carbon dioxide and carbon monoxide, under simulated sunlight. After several days, it checked whether any of that carbon had been incorporated into solid material. Some of the results again showed weak but detectable activity, as though something might have been interacting with the gases. The third test, known as gas exchange, was designed to check for metabolic reactions that might release or absorb gases like oxygen or carbon dioxide. The experiment added nutrient-rich water to the soil and monitored changes in the surrounding atmosphere. When the test was run, there were small but noticeable shifts in gas levels, signals that could be consistent with biological activity, though not proof of it. At first, these results seemed extraordinary. On Earth, similar chemical reactions would almost certainly mean one thing: life. But science demands careful proof, and NASA scientists were cautious. The final experiment, the gas chromatograph mass spectrometer, was built to look for organic molecules themselves, the carbon-based building blocks of life. When it analyzed the Martian soil, the results came back negative. Not a single organic molecule was detected. It was a shocking contradiction. How could the soil show apparent signs of biological activity if it contained no organic compounds at all? The Viking landers seemed to be sending mixed messages, reactions that looked biological, but chemistry that looked lifeless. Some scientists believed the results proved life existed on Mars. Others argued that strange chemical reactions in the soil, perhaps caused by strong oxidants or ultraviolet radiation, could be producing the same signals without life. Mars, it turned out, was not only dry and cold, but chemically reactive. Its surface might contain compounds that mimic life's effects while actually destroying organic material. What was thought to be a sign of microbes might instead be the fingerprint of an alien chemistry that Earth scientists had never encountered. Over the following years, NASA leaned toward the cautious interpretation. The official conclusion was that Viking had not found convincing evidence of life. The results were fascinating, but inconclusive. The lesson was clear. Finding life beyond Earth would not be simple. The universe could play tricks on even the best-designed instruments. What looked like a biological signal could turn out to be chemistry, and what seemed like emptiness could hide complexity we did not yet understand. The Viking experience made NASA far more careful in how it approached future missions. But despite the uncertainty, Viking left a lasting legacy. It proved that landing safely on Mars was possible, that machines could operate in its harsh environment and return data across millions of kilometers. The images alone changed how humanity saw the red planet. Mars was no longer a place of fantasy. It was a real world, one that could be touched, studied, and explored. The Viking missions also laid the foundation for decades of research that would follow. Every Mars mission since, from Pathfinder to Curiosity, Perseverance, and beyond, has built upon what Viking started. Its instruments, its methods, and even its mistakes became lessons that shaped the future of planetary exploration. The puzzling Viking data also sparked new ideas about how to search for life. If Mars's soil chemistry could destroy organic molecules, then perhaps those molecules were preserved elsewhere, underground, beneath rocks or in ancient sediments protected from radiation. Later missions began looking for indirect evidence: minerals formed in the presence of water, traces of methane in the atmosphere, and carbon compounds hidden in the soil. NASA's approach shifted from direct life detection to understanding habitability, asking not, "Is there life?" but "Could life survive here?" This change in thinking was born from Viking's ambiguity. Before searching for biology, we first needed to understand the environment that life would need to endure. Even decades later, the Viking results continue to be debated. Some researchers, including Gilbert Levin himself, maintained until the end of his life that the labeled release data did in fact show signs of life. Others pointed to later studies suggesting that perch lorates, highly reactive salts discovered on Mars long after Viking, could have caused the same reactions chemically. It is possible that Viking's instruments were both too sensitive and not sensitive enough, detecting real reactions but unable to tell their true origin. The truth remains uncertain, suspended between chemistry and biology. The Viking missions did not give us a clear answer, but they transformed Mars from a distant point of light into a world of possibilities, one that could challenge our assumptions and expand our understanding of life itself. When Perseverance drills into ancient rocks in Jezero Crater, when it seals small samples for future return to Earth, it is finishing what Viking began. The search continues, but the lessons remain the same. Be careful, be humble, and expect the unexpected. Lessons from a false dawn. In the summer of 1996, NASA announced something that made headlines across the world. A team of scientists believed they had found evidence of ancient life on Mars, not from a spacecraft or a rover, but from a rock that had fallen to Earth. The rock, known as ALH 84001, was a meteorite unlike any other. It had been discovered 12 years earlier in the Allen Hills region of Antarctica, buried in the blue-white ice of the southern continent. It was small, only about the size of a loaf of bread, and it looked ordinary enough to the eye. But inside, it held a story that would reignite the question that had haunted NASA since Viking. The meteorite had been blasted off the Martian surface millions of years ago, likely by the impact of another asteroid. It drifted through space for eons, before finally landing on Earth about 13,000 years ago. When it was identified as Martian in origin, it became part of NASA's growing collection of planetary samples. For years, it sat quietly in storage until scientists began taking a closer look with newer instruments. What they found would shake the scientific world. Under powerful electron microscopes, researchers discovered tiny, oval-shaped structures inside the meteorite. They looked like fossilized bacteria, microscopic worms, or tubes that seemed eerily familiar. Alongside these shapes were chemical traces, organic molecules, and mineral patterns that on Earth often form in the presence of living organisms. The lead scientist, David McKay of NASA's Johnson Space Center, and his colleagues believed they might have found the first evidence of life beyond Earth, ancient microbes that once lived on Mars billions of years ago and had left their traces in stone. When NASA made the announcement, it was a global event. The image of the meteorite appeared on the front page of newspapers everywhere. President Bill Clinton even addressed the nation from the White House lawn, saying that if the discovery was confirmed, it would be one of the most astonishing insights into the history of life. For a moment, the world seemed united in awe. The idea that we might not be alone, that life had once stirred on another planet, felt closer than ever. For NASA, it was a vindication of decades of effort and hope. After years of silence following Viking's uncertainty, this meteorite felt like the breakthrough everyone had been waiting for. But science is rarely settled by a single discovery, and in the years that followed, excitement gave way to skepticism. Scientists around the world began examining the data, testing the samples, and debating the conclusions. The more they looked, the less clear the evidence became. The tiny structures that had been called fossilized bacteria were far smaller than any known living cell on Earth. So small, in fact, that it seemed impossible for them to contain the machinery of life. Some researchers argued that similar shapes could form naturally through chemical and geological processes. The so-called organic molecules could also be explained by contamination from Earth, or by non-biological reactions that occurred on Mars itself. Slowly, the once thrilling image of Martian microbes began to blur into uncertainty. The debate grew fierce. Some held fast to the idea that ALH 84001 contained traces of life, insisting that the combination of shapes, chemistry, and magnetite crystals was too coincidental to be purely natural. Others saw it as a classic case of wishful thinking, scientists seeing patterns they wanted to see. As the evidence was reanalyzed, it became clear that every clue could be interpreted in more than one way. The mineral formations, once thought to be bacterial fossils, were later shown to be consistent with non-biological processes that happen at high temperatures. The magnetite crystals that seemed so biological turned out to form in other meteorites too, without any involvement of life. Even the organic molecules were found to be ambiguous, as similar compounds can form in space through purely chemical means. The story of ALH 84001 revealed the tension between curiosity and caution, the same balance that had challenged the Viking missions decades earlier. The excitement of possibly finding life had made even experienced scientists vulnerable to confirmation bias, the subtle tendency to favor results that fit what one hopes to find. The rock had seemed to whisper an answer, and it was easy to believe it, if only for a moment. But science must move slower than excitement. It must test, doubt, and retest until no other explanation remains. To declare that life had been found, the proof would need to come from multiple independent signs, chemical, geological, and biological, all pointing to the same conclusion. Anything less risked mistaking the unfamiliar for the extraordinary. The fallout from the meteorite debate reinforced the value of patience, collaboration, and peer review. Rather than rushing to announce new findings, scientists began emphasizing transparency and replication. Each discovery would have to survive not only internal scrutiny, but also global testing by independent teams. The process became slower but stronger, built on a foundation of collective verification. In many ways, this cautious mindset became the cornerstone of modern astrobiology. At the same time, the ALH 84001 episode sparked new energy in the field. Even if the meteorite had not truly contained life, it had proven that Mars could preserve a record of its past in rocks that eventually reach Earth. This realization opened new possibilities for research. If one Martian rock could travel here naturally, perhaps we could one day collect them deliberately, samples gathered by robotic missions and returned for study in Earth's laboratories. The idea of sample return began to grow from a distant dream into a concrete plan. The meteorite, even in its controversy, became a symbol of how close we might be to finally answering the question that had driven NASA from the beginning. The incident also highlighted how public the search for life had become. In the age of global media, scientific discoveries no longer lived quietly in academic journals. They were broadcast instantly, carrying the weight of public hope. For NASA, this brought both opportunity and pressure. The agency had to communicate science in a way that was honest, but also inspiring, cautious, but not cold. The balance between wonder and evidence became as important as the research itself. The lesson of ALH 84001 was not just scientific, it was cultural. It showed that the world wanted answers, but the true answers take time. Years later, when new missions like the Mars rovers and orbiters began searching for signs of water, organic molecules, and habitable conditions, they did so with the lessons of Viking and ALH 84001 in mind. They were designed to avoid false positives, to rule out every non-biological explanation before even suggesting life. Each test, each sensor, and each camera was built with skepticism as a guiding principle. Even now, ALH 84001 sits in NASA's collection, stored carefully in a clean room, still a subject of study. Scientists continue to examine it with newer technology, using tools that didn't exist in the 1990s. Occasionally, new data reopens the debate, showing that the line between chemistry and biology is not as clear as we once thought. The rock remains silent, its secrets trapped in its mineral layers, but its story continues to shape how NASA thinks about discovery. The rise of astrobiology as a science. By the late 1990s, after the lessons of Viking and the controversy of the Martian meteorite, NASA found itself standing at a crossroads. The question was no longer simply, is there life out there? It had become broader, more thoughtful. Where could life exist and what would it need to survive? That shift in thinking marked the beginning of something new. A new science began to take form, one that would unite astronomy, biology, chemistry, and geology under a single purpose. It was called astrobiology, and NASA would be at its heart. Astrobiology began with a simple realization. To search for life, we first had to understand what life really was. For decades, scientists had thought of life in Earth-centered terms, something that required oxygen, sunlight, and mild temperatures. The search for alien organisms had largely followed that narrow template. But in the 1980s and 1990s, discoveries on our own planet began to overturn that idea. Biologists exploring some of Earth's harshest environments started finding living organisms in places that seemed utterly uninhabitable. Boiling volcanic springs, deep ocean vents, frozen glaciers, and pools of toxic acid. In Yellowstone National Park, researchers found bacteria, later dubbed extremophiles, thriving in water hot enough to cook an egg. At the bottom of the ocean, near hydrothermal vents, entire ecosystems lived in darkness, feeding on chemicals released from the Earth's crust rather than sunlight. In Antarctica, microbes were discovered frozen into ice, alive but dormant, waiting for rare thaws to reawaken. Even in caves filled with poisonous gases or deep underground, life persisted in forms no one had imagined. These discoveries stretched the boundaries of what it meant to be alive. They showed that life was not fragile. It was adaptable, resilient, and capable of surviving under extreme stress. The implication was clear. If life could thrive in Earth's most hostile corners, then maybe it could survive elsewhere in the universe too. For NASA, this meant that the search for life no longer needed to focus only on Earth-like worlds. The possibilities multiplied overnight. Moons like Europa and Enceladus, once considered barren ice balls, suddenly seemed promising, because beneath their frozen crusts lay oceans heated by tidal forces. Even the clouds of Venus and the methane lakes of Titan could not be dismissed. The discovery of extremophiles on Earth had rewritten the map of habitability across the solar system. Astrobiology took shape around this new understanding. In 1998, NASA formally established the Astrobiology Institute, a virtual research organization that brought together scientists from across disciplines and institutions. Instead of focusing on hardware or missions, the institute focused on questions. What are the conditions for life? How does it begin? How does it adapt? And how can we recognize it when we find it? It united astronomers who studied distant planets with biologists who analyzed microbial DNA, chemists who investigated organic molecules in space, and geologists who examined ancient rocks on Earth for signs of early life. Each field brought a piece of the puzzle, and together they began to paint a picture of life as a cosmic phenomenon. The study of Earth's extremophiles became central to this effort. By understanding how organisms survived in boiling acid or beneath Antarctic ice, scientists could design better experiments for Mars and other worlds. They learned, for example, that some microbes could live without sunlight, drawing energy from chemical reactions instead. That meant life might exist deep underground on Mars or in the dark oceans beneath Europa's ice. Other microbes could survive intense radiation, high salinity, or near vacuum conditions, traits that made them natural analogues for extraterrestrial environments. In a sense, these Earth organisms became stand-ins for alien life, teaching NASA what to look for and how to look for it. Astrobiology also changed the way NASA thought about exploration. When spacecraft like Galileo and Cassini began exploring the outer solar system, their instruments were tuned to detect water, heat, and organic molecules, the ingredients of life. When the Mars rovers were designed, their primary goal became not to find life directly, but to study habitability, to learn whether Mars had once been warm and wet enough for microbes to survive. The new approach was about building the case, layer by layer, before claiming any discovery. At the same time, NASA began looking beyond the solar system. Advances in telescope technology made it possible to detect planets orbiting other stars, exoplanets, and astrobiology played a central role in interpreting what these worlds might be like. The discovery of planets in the so-called habitable zone, where liquid water could exist, suddenly gave scientists targets for future missions. For the first time, humanity had a way to search for life not just in our own cosmic backyard, but across the galaxy. Astrobiology provided the framework for understanding what to look for: chemical signatures in atmospheres, temperature ranges, and the presence of water or methane. It also helped scientists define what life-friendly meant, not as a rigid set of Earth-like traits, but as a spectrum of possibilities. In the years that followed, astrobiology expanded from a scientific idea into a movement that reached classrooms, laboratories, and observatories across the world. It became a field where planetary science met evolutionary biology, where the study of microbes merged with the study of stars. For young scientists, it offered something rare: a chance to work at the frontier of both science and philosophy, to explore not only how life works, but what it means in a universal context. NASA's support helped legitimize this work, turning it from speculation into structured research. The agency funded programs to simulate alien environments, to study ancient Earth as an analog for early Mars, and to develop new tools that could one day detect biosignatures in distant planetary atmospheres. Astrobiology also encouraged a deeper appreciation of Earth itself. As researchers searched for the limits of life elsewhere, they came to see how extraordinary our own planet was. Its stability, its chemistry, its balance of energy, all the factors that make it habitable, are rare gifts in a universe that seems mostly empty and cold. To understand how life might survive elsewhere, we first had to understand how it survives here. The same science that might one day discover alien organisms also helped us understand the fragility of Earth's ecosystems, the effects of climate change, and the resilience of life in the face of adversity. As astrobiology matured, it also began to influence how NASA communicated its goals. The idea of searching for life gave the agency a clear narrative that connected missions across decades. A probe studying Europa's icy crust, a telescope analyzing exoplanet atmospheres, a rover sampling Martian rocks. They were all part of the same story. Each mission became a chapter in humanity's larger search for life and understanding. This coherence gave NASA's exploration program both scientific focus and emotional power. On Earth, life is based on carbon and water, but could there be other chemistries, other biologies that follow different rules? Astrobiologists began exploring these possibilities, modeling what silicon-based life or ammonia-based ecosystems might look like. They even began considering the potential for life to exist in forms that defy biology, perhaps as self-organizing chemical systems, or even digital life within alien environments. These ideas pushed science beyond its traditional boundaries into a realm where evidence and imagination worked hand in hand. Life as we don't yet know it. NASA's scientists had long worked with a simple operational definition. Life is something that uses energy, reproduces, evolves, and maintains internal order against the pull of entropy. It's a definition that works well for Earth, but the universe might not share our assumptions. On our planet, life depends on carbon as its backbone and water as its solvent. DNA and RNA carry the instructions for replication, and proteins handle the chemistry of survival. Yet these are products of a specific history on one world. If life arose elsewhere under different conditions, it might have chosen a different path entirely. It might use another element to build its structures, or a different liquid medium, like methane or ammonia. The difficulty lies in the fact that all of NASA's instruments are made by humans. They are reflections of our own biology and understanding. A mass spectrometer on Mars, for example, is designed to detect organic molecules like carbon compounds and amino acids. But if an alien form of life used completely different chemistry, say molecules built around silicon or patterns of mineral structures, it might leave no trace that our machines could recognize as biological. To them, it would just look like rock or dust. Even if it were alive in its own sense, breathing and metabolizing in ways beyond our comprehension, we might never know it. Could life already exist in our solar system, right in front of us, but remain invisible simply because we don't know what to look for. How could NASA design instruments capable of detecting life as we don't yet know it? To do so, the agency began reaching beyond biology into the study of complexity itself. Instead of searching for specific molecules, scientists started asking whether there might be universal signatures of living systems, patterns that reveal organization, adaptation, or purposeful chemistry, no matter what materials are involved. They began to think of life not as a list of ingredients, but as a process. Some scientists proposed that life in any form might show certain patterns, the use of energy gradients, the concentration of rare elements, or the production of molecules that are too complex to form by chance. Others suggested looking for entropy reduction, local pockets of order in environments that should otherwise be chaotic. These are subtle signs, not easily measured, but they could provide a way to recognize something alive without knowing what it is made of. One of the earliest attempts to broaden this search came through studies of Saturn's moon Titan. When the Cassini spacecraft and its Huygens probe explored Titan in the 2000s, they revealed a world completely alien to Earth, one where rivers and lakes are made of liquid methane, and the rain that falls from the orange sky is hydrocarbons, not water. The surface is hundreds of degrees below freezing, far too cold for Earth-like life. But Titan's chemistry is rich and dynamic. Its atmosphere is thick, filled with complex organic molecules that constantly react and rearrange. This led NASA to fund experiments that simulated alien chemistries in the lab. At the Jet Propulsion Laboratory, researchers began mixing gases, ices, and minerals under conditions similar to those found on distant worlds. They wanted to see whether complex self-organizing molecules could emerge in unexpected ways. In some cases, they did. Chemical systems that formed membranes, reacted to stimuli, and even sustained repeating cycles of activity, though not in the same way as living cells. These experiments blurred the line between the living and the non-living, suggesting that life might not be a category but a continuum, a spectrum of complexity that gradually crosses into self-sustaining behavior. To account for this, NASA began rethinking how to build missions. Future instruments would not just look for specific compounds, but would measure broader signs of chemical disequilibrium, environments where something is constantly maintaining imbalance. On Earth, that imbalance comes from life, plants creating oxygen, animals consuming it, and microbes cycling carbon. In a lifeless world, those processes stop and chemistry falls into stability. By looking for worlds that remain out of balance, NASA could detect something active, even if it didn't match Earth's biology. This principle became part of the design for missions like the James Webb Space Telescope, which analyzes the atmospheres of distant exoplanets for combinations of gases that shouldn't exist together unless something is producing them. Some researchers proposed that life should be defined by its capacity to evolve, to use information to adapt and persist. Others argued that life might best be understood as a self-sustaining system that can change its environment in pursuit of survival. These ideas stretched the boundaries of science into questions once considered purely abstract. But in NASA's work, philosophy became practical. How one defines life determines how one builds the instruments to find it. As this approach deepens, it has begun to blur another line, the one between biology and chemistry, between what is alive and what is merely active. Perhaps life is not a special category at all, but a natural stage of complexity that emerges wherever conditions allow. If that is true, then life may be not a rare exception, but an inevitable outcome of the universe's tendency towards structure. In that view, our own existence becomes part of a much larger pattern, a single example of matter learning to organize itself, to sense, to think. Bureaucracy among the stars. NASA is, at its core, a government agency, a public institution bound by budgets, politics, and bureaucracy. Every mission, every experiment, and every statement must pass through layers of oversight and review. Even when its scientists stand at the edge of discovery, NASA must speak carefully, because it is accountable not only to the scientific community, but to Congress, the media, and the taxpayers who fund it. The search for life, perhaps the most thrilling pursuit of all, must therefore unfold within a framework of restraint. This bureaucratic nature has shaped NASA since the day it was founded. Born out of the Cold War, the agency was created not just to explore, but to demonstrate national capability. It inherited a culture where precision mattered as much as ambition, and where every decision had to be justified in both technical and political terms. Over the decades, that culture evolved into one defined by methodical planning, risk assessment, and cautious communication. NASA's scientists are not free to say, "We think we found life." They must instead say, "We have found data consistent with possible biological activity, though abiotic explanations cannot yet be ruled out." Within NASA's walls, this process can be slow and frustrating. A scientist may discover an unusual signal or chemical signature that could hint at life, but before speaking publicly, they must run countless checks, repeat experiments, and rule out every alternative explanation. Reports move through committees, data are reviewed by external panels, and language is scrutinized for accuracy and neutrality. What might begin as a thrilling moment of potential discovery becomes months or years of verification. To the public, this can make NASA seem overly cautious, even secretive. But to the agency, it is a matter of integrity. It would rather be late than wrong. The same caution extends to how NASA designs its missions. Because funding comes from Congress, every dollar spent must be justified in terms of clear, measurable objectives. The search for life is one of the most compelling missions imaginable, but also one of the hardest to define. How do you measure success if the result might be inconclusive? Bureaucracy demands clear deliverables, timelines, and outcomes. Yet science, especially frontier science, rarely works that way. As a result, NASA often frames its missions not as direct searches for life, but as studies of habitability. It's a safer term, scientifically cautious and politically comfortable. Instead of promising discovery, it shifts the narrative to studying environments. It is, in a sense, the bureaucratic translation of curiosity. Press releases are written with layers of review, ensuring that no single phrase overstates what the data can support. Scientists inside the agency often joke that NASA's favorite word is consistent. Rather than saying something proves life exists, they say it is consistent with the possibility of life. When an agency relies on yearly appropriations, public and congressional confidence becomes its lifeline. A single misstep can lead to budget cuts, investigations, or even the cancellation of future missions. At the same time, NASA's conservatism contrasts sharply with the boldness of the private sector. Independent researchers, startup ventures, and citizen scientists often speak in language NASA cannot use. They make claims about microbial life in the clouds of Venus, or fossils in Martian rocks, or biosignatures in distant exoplanets. Some of these claims are genuine attempts at discovery, others are speculative or even sensational. But they spread quickly across headlines and social media, capturing public imagination. The agency often finds itself in an awkward position, protecting the integrity of science while competing with voices unbound by the same rules. NASA operates under public scrutiny. Every email, every budget line, every research grant can, in theory, be examined under the Freedom of Information Act. That transparency ensures accountability, but it also makes the agency cautious. Even the hint of impropriety or exaggeration can trigger political backlash. Private companies, in contrast, can take risks and pivot quickly. They can chase attention and investment with bold promises, while NASA must move slowly, anchored by process and oversight. Yet, paradoxically, it is this very restraint that gives NASA its authority. In a world of speculation, it is the quiet voice of confirmation that ultimately matters most. This culture of caution also shapes NASA's relationships with its scientists. Many researchers working on astrobiology are not full-time NASA employees, but contractors or academics funded through NASA grants. These scientists often walk a delicate line between curiosity and compliance. They may believe they have found something extraordinary, but before they can speak, their data must pass through institutional filters. Sometimes this can lead to tension. Ambitious scientists want to share their findings with the world. NASA wants to protect its reputation. The result is a slow, deliberate rhythm of discovery that can feel at odds with the fast pace of modern media. NASA's administrators have long known that the agency's survival depends on maintaining bipartisan support. Space exploration has always been both a scientific and a symbolic endeavor, a demonstration of national capability. The Apollo program was born not from a love of astronomy, but from geopolitical competition. After the moon landings, when Cold War urgency faded, funding for human exploration fell sharply. In the decades that followed, NASA had to reinvent its narrative. The search for life became one of the few themes broad enough to unite scientific curiosity with public interest. But even then, it had to be framed carefully to avoid sounding like science fiction. NASA could inspire, but it could not promise. Funding politics add another layer of complexity. Every new mission proposal competes against dozens of others, all vying for limited resources. Lawmakers must be convinced that the mission serves national interests, advances science, and has a clear chance of success. Searching for life sounds exciting, but it also carries risk. What if billions are spent and nothing is found? To justify such investment, NASA often embeds the search for life within broader scientific goals, studying climate, planetary geology, or solar system evolution. This framing makes the mission appear more stable and less speculative. The politics of funding also influence the global partnerships NASA forms. International collaboration helps distribute costs and risks, but it also introduces diplomatic considerations. Missions must be negotiated with space agencies from Europe, Japan, and elsewhere, each with its own priorities. Political relationships, sometimes cooperative, sometimes tense, can determine whether a mission proceeds or stalls. NASA has become adept at weaving scientific goals through the fabric of diplomacy, framing joint missions as tools of peace and collaboration. This approach not only shares financial burdens, but also makes the agency's work more resilient to domestic budget shifts. Within this system, a quiet resilience persists. Bureaucracy may slow NASA down, but it has also given it endurance. Its methods create a kind of institutional humility, a recognition that extraordinary claims require extraordinary evidence. Still, inside the agency, there are moments when that bureaucratic caution feels like a cage. Scientists who spend decades studying Mars, Europa, or Enceladus often speak of the tension between their curiosity and the institution's restraint. They are aware that behind every press release lies a far more emotional reality, but they also know they cannot say it out loud until the data are irrefutable. And so the search continues, not only in the heavens but within the walls of the agency itself. When public optimism meets scientific caution, whenever NASA announces even a small discovery related to Mars, exoplanets, or distant moons, the reaction on Earth is electric. Headlines flare across every news site. Social media lights up with speculation. The agency has learned over decades of experience that words can carry as much weight as data. A single phrase, taken out of context, can become a global sensation. When scientists talk about liquid water on Mars, for example, they mean thin, salty flows that might briefly form under very specific conditions. But to the public, it sounds like oceans waiting beneath the surface, teeming with alien life. NASA's media teams now understand that every discovery is also a communication event. The language of the press release is reviewed by scientists, communicators, and even lawyers. There's a rhythm to how discoveries unfold. A research team finds something strange, a chemical trace, a pattern in data, a spike in a graph. It's exciting, but the rule is always to question it. Teams double-check instruments, test for contamination, compare readings and repeat measurements. Months or even years can pass before a paper is published. But the moment that paper appears, journalists and the public often jump straight to the most dramatic interpretation. NASA, aware of this, now tries to control the pacing of information. They release visuals, diagrams, and explanations that place results in context. They hold press conferences where scientists emphasize what they don't yet know. Public enthusiasm is a resource, NASA depends on it to justify its budget, to inspire students, to motivate international cooperation. But if that enthusiasm turns into disillusionment, if the public feels misled, it can erode trust not only in NASA, but in science as a whole. One example that captures this struggle came during the discovery of Kepler 452b, a planet described as Earth's cousin. When the announcement was made, the world reacted as if NASA had just found another Earth, with oceans and forests waiting for us. In reality, the planet was simply similar in size and orbit, with conditions that might be right for liquid water. NASA's scientists had to spend weeks explaining that Earth-like doesn't mean Earth twin. The story still inspired millions, but it also showed how easily context can be lost when the words are simplified for mass appeal. In more recent years, NASA has tried to refine how it communicates discovery. They now include confidence levels in press materials, visual aids that show how certain or uncertain the findings are. They collaborate with science communicators who specialize in public education, aiming to make caution feel as exciting as confirmation. This approach extends to how NASA trains its scientists to talk to the public. Workshops and media briefings teach them to use clear, relatable language without giving up accuracy. They learn to explain why a null result, a lack of evidence for life, is still valuable, because each time they don't find life, they refine where and how to look next. They remind audiences that patience is part of progress. The story of astrobiology isn't a single breakthrough, but a growing understanding built layer by layer. The quiet partner, SETI, and NASA's distance. For most people, the idea of NASA searching for life beyond Earth brings to mind more than just microbes. It brings to mind the big question, the one about intelligent beings looking back at us. Yet inside the agency, there's a very clear distinction between looking for biology and looking for intelligence. One is an accepted part of planetary science. The other, despite its deep connection to human imagination, exists mostly outside of NASA's walls. That difference is the reason why another organization, the SETI Institute, quietly became the world's main listener for alien technology, while NASA kept its focus on alien biology. In the early decades of the space age, there was no such divide. During the 1960s and 1970s, NASA supported several early projects that tried to listen for radio signals from other civilizations. The idea was that if intelligent beings existed elsewhere, maybe they used radio waves, just as humans did. Radio astronomy was new, and the universe suddenly looked full of possibilities. Scientists like Frank Drake and Carl Sagan helped design these early listening experiments, blending solid physics with deep philosophical curiosity. The public was fascinated, and for a time, the search for extraterrestrial intelligence sounded like a natural part of NASA's mission. But as decades passed, enthusiasm for direct searches faded inside the agency. The turning point came in the early 1990s with a project called the High Resolution Microwave Survey, or HRMS. It was NASA's most ambitious attempt to scan the skies for artificial radio signals. Using powerful antennas like those at Arecibo in Puerto Rico, the program planned to listen to millions of frequencies, searching for anything that didn't sound like a natural source. It was a technical marvel, combining the best of computing and astronomy at the time. But less than a year after it launched, Congress shut it down. The cancellation wasn't because of scientific failure, it was political optics. Some lawmakers mocked the project as a waste of money looking for little green men. To them, the very phrase "search for extraterrestrial intelligence" didn't sound like real science. In an era of tightening budgets, funding something that could so easily be misunderstood wasn't worth the risk. Overnight, NASA was forced to cut its ties with any program that could be seen as a hunt for aliens. The event sent a clear message: searching for microbes was acceptable, searching for civilizations was not. Microbes could be studied through chemistry, geology, and planetary science. Civilizations, on the other hand, brought up uncomfortable questions about religion, politics, and philosophy, questions no government agency wanted to be seen as answering. From that point on, NASA avoided the term SETI altogether. The search for life continued, but now under a different name and focus, astrobiology. But while NASA stepped back, the scientists didn't stop. In 1994, a group of researchers, including Jill Tarter and Frank Drake, founded the SETI Institute in California. It was designed to continue what NASA could no longer do, to listen independently for signs of intelligence among the stars. Funded mostly through private donations and partnerships, the Institute built its own radio observatories, such as the Allen Telescope Array, specifically designed for SETI research. It was, in many ways, NASA's unofficial partner, a quiet collaborator working outside the limits of public funding. Even though NASA and SETI officially operate separately, their missions overlap in spirit. Both are driven by the same question, but they approach it from different directions. SETI searches for structured, repeating signals, patterns of light or radio that nature couldn't easily produce on its own. If NASA finds fossils, SETI hopes to find transmissions. The difference might seem small, but it defines the kind of evidence each organization considers credible. For NASA, a signal from another civilization would be a discovery of enormous weight, but also one that sits outside its scientific framework. Its missions are designed to detect molecules, not messages. Its instruments analyze soil, atmosphere, and radiation, not encoded information. So even if a signal from space were detected, it wouldn't be NASA that confirmed or studied it. That responsibility has quietly passed to independent institutions like SETI. Still, the relationship between NASA and SETI isn't cold or hostile. It's more like a quiet understanding between partners who share the same dream but must play by different rules. NASA supports research that indirectly helps SETI, developing new sensors, telescopes, and data analysis tools that could one day be used to search for artificial signals. It funds exoplanet missions like Kepler and TESS, which identify planets where SETI might point its antennas. In return, SETI uses NASA's discoveries as a roadmap, targeting newly found star systems that could harbor intelligent life. The two organizations also share information informally. When SETI scientists analyze data that touches NASA's areas of study, such as atmospheric chemistry or planetary climate, they often collaborate through joint conferences and workshops. Yet officially, NASA maintains its distance. Its public documents describe life searches in purely biological terms. The words extraterrestrial intelligence appear rarely, if ever. The agency knows how fragile public trust can be, and how quickly the line between science and sensationalism can blur. The SETI Institute, free from those constraints, can speak more openly about the possibility of advanced civilizations, about the implications of finding them, or even the ethics of contact. It can host public events discussing what a techno-signature might look like, whether a laser beam, a Dyson sphere, or a pattern of light in a distant atmosphere. Where NASA must remain cautious, SETI can speculate. Yet despite the separation, NASA's fingerprint is everywhere in SETI's work. The same precision, the same emphasis on verification and data quality comes from the culture NASA helped create. SETI scientists follow the same discipline when handling potential signals. Every possible source of human interference, satellites, aircraft, ground-based noise, must be ruled out before a signal is even considered unusual. Over time, the boundary between NASA's astrobiology and SETI's techno-signature research has begun to soften again. The change became more visible with projects like Breakthrough Listen, a privately funded initiative launched in 2015 with support from entrepreneur Yuri Milner and physicist Stephen Hawking. Breakthrough Listen's goal was to conduct the most comprehensive search for extraterrestrial signals ever attempted, using some of the world's largest radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia. While not a NASA project, Breakthrough Listen relied on data and technical expertise that often intersected with NASA's missions. Breakthrough Listen scientists worked with NASA's exoplanet researchers to cross-match those targets with known planetary systems. The collaboration helped avoid duplication, optimized telescope schedules, and shared computational resources. The result was an ecosystem where public and private researchers worked side by side, each adding to the other's capabilities. In recent years, NASA has started funding small studies about how to detect signs of technology, not as active searches, but as theoretical groundwork. These are often labeled techno-signature studies rather than SETI, a subtle shift in language that allows the agency to explore the topic without reopening old controversies. It's a cautious re-entry into territory it once abandoned, guided by the idea that understanding potential signs of technology is, in itself, a scientific question. This renewed openness also grew out of technological necessity. Modern space exploration produces mountains of data, images, spectra, time series graphs, and more. Artificial intelligence and machine learning are now essential for sorting through it all. SETI researchers were among the first to apply these methods, training algorithms to recognize patterns in radio signals that human eyes might miss. NASA, facing similar challenges in exoplanet and atmospheric research, began to collaborate with these same data scientists. That inclusivity extends beyond professionals. One of the most remarkable aspects of this new era is how ordinary people, students, hobbyists, and volunteers are helping to search the universe. Through platforms like Zooniverse and SETI at home, citizen scientists analyze telescope data from their own computers, flagging anomalies or patterns that might otherwise go unnoticed. SETI at home, in particular, became a cultural landmark in the late 1990s and early 2000s. Millions of users donated spare computing power to sift through radio signals collected by observatories, each one contributing a small piece to a massive global analysis. Though the project officially ended its active phase in 2020, its spirit continues in new citizen science efforts connected to exoplanet studies and spectral data classification. SETI continues its patient vigil, listening to the sky with instruments far more sensitive than anything available during NASA's early days. The search has become quieter and more methodical. There are no dramatic announcements or false alarms, just years of slow, careful observation. Most of the time, the signals they detect are quickly identified as satellites, interference, or natural cosmic phenomena. But the scientists keep listening. NASA watches this work from a distance, aware that if that faint, unmistakable signal ever arrives, it would change everything. It would bridge the gap between biology and technology, between microbes and minds. And though the agency may not lead that search, it would be among the first to help understand what comes next. The Great Silence and the Fermi Paradox. In the decades since NASA began its search for other worlds, the universe has turned out to be far more crowded than anyone once imagined. The first exoplanet orbiting a sun-like star was discovered in 1995. Since then, missions like Kepler have revealed thousands more. Many of these worlds are roughly the same size as Earth. Some orbit within the habitable zone. Every year, the count grows, and with it the sense that Earth cannot be unique. Statistically, there should be millions of planets capable of hosting life. And yet, when we listen, the universe remains silent. That silence has a name, the Fermi Paradox. It was first phrased as a simple question: if life is common, where is everybody? The paradox sits at the intersection of expectation and reality. Every discovery of a new Earth-like planet raises the odds that someone else is out there, but every year of radio silence makes that possibility harder to believe. For NASA, the Fermi paradox is not treated as a mystery to be solved through philosophy, but as a problem that can be explored through data. The agency's scientists don't assume the absence of evidence means the absence of life. They treat it as a question about probability, detectability, and timing. One explanation the data points toward is distance. The universe is enormous beyond easy comprehension. Even within our own galaxy, stars are separated by light years, vast stretches of space that radio waves take years or centuries to cross. If an alien civilization existed 10,000 light years away and sent a message, it might still be traveling toward us now, unseen and unheard. Our instruments, no matter how sensitive, can only scan a small fraction of the sky at any one time. It's possible that signals are out there, but we simply haven't been looking long enough or wide enough to catch them. Another factor is time. Civilizations, including our own, may not last long in cosmic terms. Humanity has been capable of broadcasting radio signals for just over a century, a blink in galactic history. If another civilization's period of radio communication lasted only a few hundred years, the chance of our signals overlapping is very small. We could be like ships passing in the night, separated not just by distance, but by eras. NASA's studies of planetary habitability take this into account. They show that even when conditions for life exist, maintaining a stable environment for billions of years is difficult. Planets shift, climates change, stars flare and atmospheres vanish. The cosmic timescale of habitability might be shorter than we assume. Then there's the question of detectability. NASA's telescopes and instruments are designed to find signs of life, but only the kinds we understand. If other civilizations use technologies or chemistries beyond our comprehension, their signatures might pass right through our detectors unnoticed. Even radio signals, once considered universal, might not be the method of communication used elsewhere. Our search for intelligence has been built on human assumptions, and NASA's data now show how fragile those assumptions can be. Some of the most important clues come not from distant exoplanets, but from our own solar system. Mars, once thought to be lifeless, now appears to have a more complex history. There are traces of ancient rivers and lakes and methane that appears and disappears seasonally. Europa and Enceladus hold subsurface oceans that could be home to microbes. These findings show that life-friendly environments might exist in many forms, but they also underline how hard it is to confirm anything without direct evidence. NASA's rovers, orbiters, and probes have detected chemistry that could support life, but no direct proof that it's there. Life may be common, but it might also be subtle, so subtle that even with the best instruments, we only glimpse its shadows. The more NASA learns, the more it realizes how blind we still are. Our telescopes can only study a thin slice of the spectrum. Our rovers can only dig a few centimeters into Martian soil, and our radio arrays can only listen to narrow frequency bands. For all our progress, we're still early in the search. The silence may not be mysterious at all. It may simply be the sound of us not yet being able to hear. There are also scientific reasons to suspect that intelligence itself is rare. NASA's study of planetary evolution shows how fragile Earth's history has been. The planet's climate, magnetic field, and atmospheric composition all had to stay within narrow limits for billions of years to allow complex life to emerge. Catastrophic events, asteroid impacts, volcanic winters, and solar storms could have easily ended that process. If even one of those had gone differently, humans might never have appeared. So, while planets like Earth are common, Earth-like histories might be extremely rare. NASA's growing catalogue of exoplanets provides the statistics to support this. Many habitable planets orbit unstable stars or have erratic climates that make long-term life unlikely. The conditions for intelligence may require a near-perfect chain of coincidences. Still, the paradox persists because the universe is so vast. Even if only a small fraction of planets develop life and a smaller fraction develop intelligence, there should still be thousands of civilizations out there. The math suggests the odds should be in favor of contact. Some researchers inside NASA think the silence may be self-inflicted. They point to the way human technology has evolved in just a few generations, from loud, inefficient radio broadcasts to tight, directed digital communications that barely leak into space. If other civilizations follow the same path, they might be invisible to us, not because they're silent, but because their technology has become too advanced to detect. Instead of using radio waves, they might communicate through laser pulses, quantum signals, or forms of transmission we can't fathom. NASA's studies of Venus and Mars suggest that habitable worlds can become hostile quickly. Venus may once have had oceans, but became a furnace after a runaway greenhouse effect. Mars may have had lakes, but lost its atmosphere to solar wind. These examples warn that habitability is temporary. If intelligent life arises, it might face environmental collapse before it can spread beyond its home world. The Fermi paradox, from this view, is a mirror, a reflection of our own potential future. When the Voyager probes left the solar system, they carried with them the golden records. To us, they symbolize hope, but to any civilization that might one day find them, they would be almost invisible, tiny artifacts drifting through endless space. If that's how we send messages, perhaps that's also how others do. Maybe the universe is full of such faint traces, waiting in the dark, each too small or too subtle to be noticed. NASA's instruments are improving, but they are still limited to the light and radio we can perceive. There may be entire layers of communication, neutrino streams, gravitational pulses, or exotic particles that we haven't learned to read. NASA doesn't treat the paradox as proof that we're alone. It treats it as a sign that the universe still has secrets we don't yet know how to uncover. The agency's rovers, telescopes, and probes continue to gather clues, each one narrowing the gap between theory and evidence. The silence is not a wall, it's a space between questions. The statistical frontier. How many worlds could host life? The Kepler mission, launched in 2009, didn't look for planets directly. Instead, it watched for tiny dips in starlight that occurred when a planet passed in front of its star, a method known as the transit technique. For nearly a decade, it monitored more than 150,000 stars, recording these small and periodic flickers. From those flickers came a map of thousands of exoplanets, each one a confirmation that solar systems like ours were not rare but common. For the first time, scientists could begin to calculate, rather than guess, how many planets might resemble Earth. The data Kepler provided changed the Drake equation, the formula used to estimate how many civilizations might exist in our galaxy, from a speculative framework into something measurable. Before Kepler, the first few variables in that equation, such as the average number of planets per star or the fraction of planets capable of supporting life, were unknown. Now they could be derived from real numbers. Astronomers could say, with increasing confidence, that most stars likely have planets and that a significant portion of those planets orbit within their star's habitable zone. The search for life stopped being an exercise in imagination and became one in statistics. Kepler's discoveries suggested that roughly 1 in every 5 Sun-like stars could host an Earth-sized planet in the habitable zone. Since our galaxy contains about 200 billion stars, that translates to tens of billions of potentially habitable worlds. Even accounting for uncertainties, the number was staggering. The challenge was no longer finding Earth-like planets. It was determining which of those Earth-like planets actually supported life. The next step in that search came with TESS, the Transiting Exoplanet Survey satellite, launched in 2018. While Kepler focused on a small patch of the sky, TESS was designed to scan almost the entire celestial sphere, looking at the brightest and nearest stars. Its discoveries made the search more practical. The planets it found were close enough for detailed follow-up studies with telescopes like the James Webb Space Telescope. This shift marked a new stage in NASA's strategy, from counting planets to characterizing them. Now, scientists could begin to examine exoplanet atmospheres, searching for biosignatures, chemical imbalances that could hint at life. Carbon dioxide in the right proportion might suggest a stable climate. Water vapor detected in a distant atmosphere could indicate a planet capable of sustaining oceans. Each discovery built another data point for the statistical models that now guide NASA's exoplanet research. These models take the idea of the Drake equation and apply it with real precision. Instead of a simple estimate, researchers can simulate galactic populations, plugging in actual star counts, planet frequencies, and orbital patterns. They can test how variations in stellar type affect habitability, or how long atmospheres might remain stable. The numbers are still uncertain, but they are grounded in measurable physics rather than speculation. One of the most striking results from Kepler and TESS data is that smaller, rocky planets like Earth seem to be more common than gas giants like Jupiter. For a long time, astronomers assumed large planets would dominate the galaxy, but the data showed otherwise. Nature, it seems, favors small worlds orbiting close to their stars. Many of these planets are super-Earths, slightly larger and heavier than our own planet. Their gravity might help them hold thicker atmospheres, which could make them stable enough for life. These findings suggest that the galaxy might be filled with planets that are not identical to Earth, but are close enough to offer similar conditions. NASA's researchers have also begun mapping how planetary systems differ from ours. Many exoplanets orbit red dwarfs. These stars are dimmer, but can keep their habitable zones close in, meaning their planets complete orbits in just a few days or weeks. Life, if it exists elsewhere, might not require a sun-like star at all. The numbers keep changing as new data comes in. Each discovery forces a recalibration of probabilities. For example, the discovery of planets in multi-star systems, where two or more suns orbit each other, adds another layer of complexity. Could life survive in such shifting gravitational environments? The data suggest it might. Stable orbits can exist even in these systems, and some may have climates not unlike Earth's. The old assumption that life requires a single steady star now seems too narrow. This statistical expansion also affects how missions are planned. Rather than pointing telescopes at random patches of the sky, NASA now uses probability maps generated from Kepler and TESS results to identify high-likelihood targets. These maps weigh factors like star type, metallicity, distance, and radiation levels. They guide where to look next, maximizing the chances of finding biosignatures. Even with limited resources, data-driven exploration makes each observation more meaningful. Each exoplanet system is a different case study in how nature builds worlds. By collecting enough examples, patterns begin to emerge. Some planets form too close to their stars and become scorched. Others drift too far and freeze. A few sit in just the right place, the so-called Goldilocks zone. But even within that narrow band, the data show tremendous variety. Some worlds may be covered in clouds, some in oceans, and some may have continents shaped by active geology. The numbers alone can't tell us which ones are alive, but they give us the roadmap to find out. For most of human history, Earth seemed exceptional, a rare oasis in a vast desert of space. Now, the data tell a different story. Worlds like ours could be everywhere. The odds suggest that life has many chances to arise, but also many challenges to overcome before becoming detectable. NASA's use of statistics has also revealed biases in how we search. The transit method, for example, favors planets that pass directly between their star and the telescope's line of sight. That means we only detect a fraction of what actually exists. For every planet we see, there may be dozens more that remain hidden because their orbits don't line up just right. Correcting for those biases helps scientists refine their models, making estimates more accurate. Webb's infrared sensitivity allows it to analyze exoplanet atmospheres in unprecedented detail. For some of the nearby planets discovered by TESS, Webb can measure the exact mix of gases, temperature gradients, and even hints of cloud cover. We now know that the conditions for life are not rare. What remains unknown is how often those conditions actually lead to biology. NASA's scientists describe this as the next statistical step, moving from habitability to actual detection. The numbers tell us where to look, but not what we'll find. The sky, once thought to hold a handful of planets, now holds billions of possibilities, each waiting for its place in the growing equation of life. Life in the shadows of red dwarfs. When NASA's telescopes began revealing thousands of planets around distant stars, one pattern quickly stood out. The majority of them circled small, cool suns. These red dwarfs, also called M-dwarfs, are the quiet workhorses of the galaxy. They are faint, long-lived, and astonishingly common. Nearly 3 out of every 4 stars in the Milky Way belong to this class. For most of astronomical history, however, red dwarfs were largely ignored. They seemed too dim, too unstable, too alien to host life as we know it. Yet, as NASA's instruments improved, these quiet stars started to look less like cosmic backwaters and more like the best possible places to search for life. Red dwarfs are small, often less than half the mass of the Sun, and they burn their fuel slowly. Because of that, they can live for trillions of years, far longer than the universe has currently existed. From a cosmic perspective, they are nearly eternal. Their dim light means that the region where temperatures allow liquid water to exist lies much closer to the star than in systems like ours. A planet would have to orbit a red dwarf at a distance far smaller than the gap between Mercury and the Sun to stay warm enough. That closeness makes detection easier. At first, though, most scientists assumed that any planet close enough to a red dwarf to be warm would also be uninhabitable. These stars were known for their violent tempers. Many red dwarfs emit frequent stellar flares, massive eruptions of charged particles, and radiation that can strip away a planet's atmosphere or sterilize its surface. A world in such close orbit would have little protection from that onslaught. In addition, the gravitational pull between the star and the planet would cause tidal locking, the same effect that keeps one side of the Moon always facing Earth. That means one hemisphere of a red dwarf planet would be trapped in eternal daylight, while the other would remain in permanent darkness. For decades, that combination, intense flares and uneven heating, convinced researchers that these planets would be hostile to life. But simulations and climate models have shown that a tidally locked planet might not be as lifeless as once thought. If it had a thick enough atmosphere or oceans to move heat around, the difference between the light side and the dark side could be balanced. Winds and currents could circulate warmth, creating a habitable twilight band, a region of perpetual sunrise along the edge between day and night. In this strip of eternal dusk, temperatures might be mild, water could remain liquid, and life could find a foothold. In 2017, using both ground-based telescopes and the Spitzer Space Telescope, astronomers identified 7 Earth-sized planets orbiting a single red dwarf star just 40 light-years away. 3 of them lay within the habitable zone. The system immediately became one of the most studied planetary families in the sky. TRAPPIST-1's planets were all packed tightly around their small, dim sun, close enough that they could all fit within Mercury's orbit if placed around our own star. Yet their densities, compositions and orbital resonances suggested that some could have stable atmospheres and possibly even oceans. The excitement around TRAPPIST-1 sparked a deeper look at the nature of red dwarf flares. Kepler and TESS began collecting long-term light curves, continuous measurements of brightness over time from hundreds of these stars. What the data revealed was that not all red dwarfs are equally active. Some flare frequently, while others remain relatively quiet for long periods. The pattern depends on the star's age and rotation rate. Younger red dwarfs spin faster and produce more magnetic activity, leading to stronger flares. But as they age, they slow down and calm. That insight gave NASA's astrobiologists a new idea. Older red dwarfs might be ideal hosts for life. Their energy output is stable, and their long lifespans offer billions of years of steady conditions, far longer than our Sun will ever provide. Webb's infrared instruments are perfectly tuned to study the light from cool stars like red dwarfs. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere, if it has one. Webb can analyze that light to detect gases such as carbon dioxide, methane, or water vapor. Many of its early exoplanet targets have been red dwarf systems, including several of the TRAPPIST-1 worlds. The data from these observations are slowly revealing whether these small dim stars can truly support life-bearing planets or whether their radiation environments are too harsh. The evolving view of red dwarfs reflects a broader change in NASA's thinking. If life can adapt to darkness, radiation, and tidal extremes, then the galaxy's most common stars suddenly become its richest real estate. Instead of a handful of suitable suns, there might be hundreds of billions. Future observatories, such as the planned Habitable Worlds Observatory, are being designed with red dwarfs in mind. Their instruments will be able to detect smaller planets and capture the faint infrared signals these stars emit. Even the selection of nearby targets for direct imaging, attempts to photograph exoplanets directly rather than infer their presence, now heavily favors red dwarf systems. Because these stars are so dim, the contrast between the planet and the star is smaller, making detection easier. In a practical sense, red dwarfs are the universe's best laboratories for studying small rocky worlds. For most of human history, we assumed that life would need sunlight similar to our own, bright, yellow, and warm. The growing focus on red dwarfs suggests a quieter kind of world, one where the light is dim and the skies are tinted crimson. If life exists there, it would have evolved under a different kind of sun, perhaps in ecosystems built around faint, steady warmth. Still, questions remain. Red dwarf planets are bombarded with high-energy radiation, especially in their early years. Whether an atmosphere can survive those early storms is still uncertain. Some models suggest that magnetic fields could protect them, much like Earth's magnetosphere shields us from the solar wind. Others propose that volcanic outgassing could continually replenish lost gases. NASA's ongoing observations aim to measure those effects, to see whether the atmospheres of these worlds are stable over time or slowly eroded away. It's a slow process. Gathering enough light from such distant and faint systems takes months or even years. As of now, the evidence leans toward optimism. Some red dwarf planets appear to have densities and thermal properties consistent with substantial atmospheres. A few even show hints of cloud layers. While none of these signs confirm life, they suggest that the basic ingredients for habitability can persist. The fact that these systems are so numerous means that even if only a small fraction remains stable, the total number of potentially life-friendly planets is immense. The universe seems to build far more small stars than large ones, and it builds them to last. The idea that most life might dwell under red light, orbiting tiny stars invisible to the naked eye, is profound. It suggests that the universe's most common environments might also be the most habitable. For NASA, red dwarfs are now the frontier, small, quiet, and ancient, holding within their faint glow the greatest number of chances for life to exist. The Phantom of Phosphine. Lessons from Venus. In September 2020, a group of astronomers made an announcement that rippled across the world. Using powerful radio telescopes, they had detected something unexpected in the thick, toxic clouds of Venus, phosphine gas. On Earth, phosphine is rare and unstable, found mostly in places shaped by life, in swamps, in the guts of animals, and in decaying organic matter. It is not something that appears easily through ordinary chemistry. So when scientists reported its presence on our neighboring planet, many wondered whether it might be a clue to something alive, drifting in the upper atmosphere of one of the most hostile worlds in the solar system. The discovery was dramatic because Venus had long been considered almost completely uninhabitable. Its surface temperature is hot enough to melt lead, its air is made mostly of carbon dioxide, and its pressure is more than 90 times that of Earth's. Yet the idea of life on Venus was not new. Decades earlier, Carl Sagan and others had speculated that the planet's high clouds, where temperatures are milder, might offer a refuge for simple airborne microbes. The phosphine detection seemed to breathe life back into that old theory. If the gas was really there, it might mean that something biological was producing it in those clouds. The discovery had come from ground-based observations using the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Submillimeter Array, or ALMA, in Chile. These instruments detect radio waves, and phosphine has a distinct signature at a specific wavelength, a dip in the spectrum caused by the molecule absorbing light. The team behind the claim said they had found exactly that. Within days, headlines appeared across the world. Life on Venus? They asked. Possible signs of life detected on Earth's evil twin. Almost immediately, other researchers began to look at the data themselves. The signal was faint, barely rising above the noise. Some wondered if the telescope's data processing had created an artificial feature, a ghost in the system, rather than a real chemical fingerprint. Others pointed out that the conditions in Venus's atmosphere are extreme: clouds filled with sulfuric acid, intense ultraviolet radiation, and powerful winds. Could phosphine even survive in such a place? If it was there, it should quickly break apart. Something would have to be replenishing it constantly. The possibilities were intriguing, but the chemistry didn't seem to add up. NASA scientists at the Goddard Space Flight Center began running models of Venus's atmosphere to test whether natural, non-biological processes could explain the detection. They considered lightning, volcanic activity, and reactions between minerals and acids. None of these seemed capable of producing enough phosphine to match the reported signal, but that only made the situation more confusing. If the gas wasn't geological, and if biology seemed implausible, then what was happening? As more groups revisited the data, cracks began to appear in the original claim. One reanalysis suggested that the processing method used to remove noise had accidentally introduced an artificial dip at the same wavelength where phosphine was expected. When they reprocessed the data with different settings, the signal nearly vanished. Another team argued that the feature might actually belong to sulfur dioxide, a common gas in Venus's atmosphere, rather than phosphine. The line between the two molecules was subtle, but under certain conditions, sulfur dioxide could easily masquerade as phosphine in the spectral data. The phosphine story grew more complicated as follow-up observations were made. New data from ALMA, taken after recalibrating the array, showed no clear sign of phosphine. Some scientists argued that if the gas existed at all, it was at much lower levels than initially reported, perhaps too little to have any biological meaning. Others, however, maintained that there might be temporal or regional variations. Maybe phosphine appears in bursts, produced by short-lived processes like lightning or chemical storms. The debate became a tug-of-war between competing models, each using slightly different assumptions about Venus's atmosphere. NASA's involvement deepened when its planetary scientists began planning new missions to Venus. The agency's Da Vinci and Veritas missions, already under consideration, suddenly gained renewed interest. The phosphine episode had reminded everyone that Venus was still full of mysteries. Decades of focus on Mars and the outer planets had made Earth's nearest neighbor seem familiar, even dull. But now, the idea that something strange, perhaps even biological, could exist there reignited curiosity. The instruments used to detect phosphine were not designed for such faint planetary signals. They were built mainly for observing stars and galaxies, where the light is strong and the chemistry simpler. Detecting a trace molecule in a bright, complex planetary atmosphere was an entirely different challenge. The limits of the equipment, the difficulty of calibration, and the risk of overinterpreting noise all played a role. For young scientists watching the debate unfold, it became a reminder that extraordinary claims require not just extraordinary evidence, but extraordinary patience. No single telescope, no single measurement should stand alone when making claims of such magnitude. In the years since, NASA has emphasized multi-instrument validation, combining data from optical, infrared, and radio telescopes, both on the ground and in space. This approach helps ensure that any potential biosignature can be tested from multiple angles using independent methods. It's a safeguard against the kind of excitement that can momentarily outpace certainty. Even after the initial excitement faded, Venus remained under the scientific spotlight. The questions the phosphine claim raised about chemistry, habitability, and the limits of detection didn't vanish. Instead, they reshaped the conversation. Researchers began asking what other unusual molecules might exist in Venus's atmosphere and whether the planet's chemistry could produce compounds we don't yet understand. Some proposed that unknown reactions involving sulfur or chlorine might be creating fleeting molecules that mimic phosphine. Others look to the possibility that microenvironments within the clouds, perhaps inside tiny droplets of acid, could harbor reactions unlike anything seen on Earth. NASA's planetary scientists took these questions seriously. The agency began refining its plans for atmospheric probes capable of directly sampling the clouds of Venus. These future missions will carry instruments that can detect trace molecules in situ, removing the ambiguity of remote sensing. The goal is not just to confirm or deny the phosphine finding, but to build a more complete picture of Venus's complex chemistry. By doing so, NASA hopes to better understand not only Venus, but also exoplanets that might resemble it, hot, cloudy worlds that orbit close to their stars. The phosphine case also had ripple effects beyond Venus. If a gas once thought to indicate life could be confused so easily with non-biological chemistry, then the same risk applies to other gases on distant exoplanets. NASA's team studying the atmospheres of faraway worlds took note. They began building broader chemical models that include a range of false positive scenarios. The goal became not just to find life, but to learn how not to mistake the natural for the living. Mars, the most studied mystery in the solar system. Mars has always been a mirror for human curiosity. It shines dimly red in the night sky, close enough to imagine visiting, yet distant enough to remain a mystery. Since the earliest telescopic observations, when astronomers thought they saw canals carved across its surface, Mars has carried the weight of one question: could life have ever existed there? Over the decades, that question has guided countless missions, each one returning answers that only seem to deepen the puzzle. In the late 1970s, the Viking landers conducted the first direct experiments searching for life on Mars. Their results, as NASA later realized, were confusing. That early uncertainty set the tone for everything that came after. When the twin rovers Spirit and Opportunity landed in the early 2000s, their mission was more modest. Not to look for life directly, but to look for evidence that Mars had once been habitable. They drove across ancient plains and crater rims, discovering layered rocks shaped by water and minerals formed in liquid environments. These findings didn't prove life existed, but they made it clear that Mars had once offered the right ingredients for it. Curiosity, which landed in 2012, took this investigation even further. It carried instruments capable of analyzing soil and rock samples in great detail. When it drilled into the Gale crater, it found complex organic molecules, carbon-based compounds that form the backbone of all life on Earth. These weren't living organisms, but they were the chemical building blocks life would need. The excitement was tempered by lessons from the past, lessons about the danger of seeing too much in ambiguous data. One of the most intriguing clues came not from rocks, but from the air. NASA's Curiosity rover detected bursts of methane that appeared to rise and fall with the seasons, suggesting some kind of ongoing activity beneath the Martian surface. For a moment, it felt like a living world was breathing, exhaling faint traces of something organic. If they were produced by microbes, where were those microbes hiding? And if they were geological, what kind of reaction could create such rhythmic variations? No single model fit perfectly. The data seemed to hover between possibilities, as if Mars itself was teasing scientists, offering just enough to keep them searching. Then came Perseverance, the most advanced rover yet. It landed in Jezero crater in 2021, a site chosen because it once held an ancient river delta, the kind of environment that, on Earth, teems with life. Perseverance carried tools to study the chemistry of sediments, scan for signs of microbial fossils, and collect rock samples for a future return mission. The rover has found clear evidence of water's presence in the past, and it has identified rocks that might preserve microscopic textures of ancient life. But nothing definitive. NASA's scientists have become masters of reading subtle clues: the ratios of carbon isotopes, the texture of sediments, the molecular fingerprints in ancient clays. Each piece suggests that Mars once had lakes, rivers, and perhaps even an ocean. Its atmosphere was thicker, its magnetic field stronger. It may have had the warmth and stability that life needs to begin. But somewhere along the way, the planet changed. Its core cooled, its atmosphere thinned, and the water disappeared into ice or vapor. The world that might once have been alive became a frozen desert. Did life have time to start before everything collapsed? NASA's search has moved deeper, both literally and conceptually. The surface of Mars today is bathed in radiation, dry and oxidized, not ideal for preserving fragile organic compounds. So scientists now look underground. Instruments on orbiters and rovers are being tuned to detect signs of subsurface ice, potential brines, and even chemical gradients that could sustain microbes in the dark. The hope is that beneath the surface, where conditions are more stable, traces of past or present life might still remain. What makes Mars so frustrating and so captivating is that it constantly blurs the boundary between the living and the non-living. Its landscapes look eerily familiar, carved by the same forces that shaped Earth. Dry river deltas and sedimentary cliffs stretch into the distance like echoes of places on our own planet. Yet everything is frozen, silent, and ancient. When NASA's rovers send back panoramic views, there's a haunting sense that the planet remembers what it once was. You can almost imagine it breathing once, under a sky filled with clouds and rain. Part of NASA's ongoing strategy is to collect samples that can be brought back to Earth for direct study. Perseverance has already drilled and sealed cores of Martian rock, storing them in titanium tubes. A future mission, jointly planned with the European Space Agency, aims to retrieve those samples and return them home. That mission, the Mars Sample Return, represents a turning point. For the first time, scientists will be able to analyze Martian material with the full power of Earth's laboratories. The hope is that within those samples, hidden deep in ancient clays or salts, there might be unmistakable chemical traces of something that once lived. But even that possibility comes with complexity. NASA must design procedures to ensure no contamination occurs, not just to protect Earth, but to keep results pure. The protocols are precise, slow, and cautious, reflecting decades of lessons learned from earlier missions. Mars, more than any other world, sits at the crossroads of evidence and mystery. The planet looks like a place where life should have been, but it keeps its secrets locked away. It gives NASA just enough to continue the chase, but never the final proof. Beneath the ice, oceans of promise. In the late 1990s and early 2000s, data from the Galileo spacecraft orbiting Jupiter and the Cassini mission around Saturn revealed something unexpected. Despite being far from the Sun, these moons showed signs of heat and movement under their icy crusts. Cracks, geysers, and magnetic measurements all hinted that beneath their frozen exteriors, water might still be liquid. Europa, one of Jupiter's largest moons, became the centerpiece of this discovery. Its surface is a smooth, bright shell of ice marked by streaks and ridges, scars where the crust has split and refrozen. When the Galileo spacecraft flew past it, its instruments detected variations in Jupiter's magnetic field that could only be explained by a conductive layer beneath the surface. The best candidate was a salty ocean, stretching around the entire moon. Beneath perhaps 10 to 20 kilometers of ice lies an ocean twice the volume of all of Earth's combined. NASA's scientists were stunned. For decades, the rule of thumb had been simple: where there's water, there's a chance for life. And here was water, more of it than on our entire planet, protected under ice, shielded from radiation and cosmic impacts. Soon, another moon joined the conversation. In 2005, NASA's Cassini spacecraft passed close to Enceladus and captured images of massive plumes erupting from its south pole, jets of water vapor and ice crystals shooting hundreds of kilometers into space. Instruments detected salt, organic molecules, and even hints of hydrogen gas in those plumes. Hydrogen meant something was reacting deep inside Enceladus, possibly between water and rock. On Earth, similar chemical reactions near hydrothermal vents provide the energy that powers entire ecosystems. Cassini's later flybys confirmed the presence of a global subsurface ocean beneath Enceladus's icy shell. The plumes had effectively given NASA a window into that ocean, spraying samples into space for the spacecraft to catch and analyze. It was a rare gift, a natural way to study an alien sea without drilling through kilometers of ice. The composition of the plumes hinted at complex organic chemistry, possibly even conditions similar to early Earth's oceans. Ganymede, the largest moon in the solar system, also showed signs of hidden depth. Its magnetic field and surface features suggested layers of ice and liquid water stacked like a layer cake. Ice, water, ice again. While less directly studied than Europa or Enceladus, it still represents a potential world with the right ingredients. The Hubble Space Telescope even detected subtle changes in ultraviolet light from Ganymede that might indicate water vapor escaping from cracks in its crust. What makes these worlds so compelling isn't just that they have water, it's the kind of water they have. On Earth, open oceans are constantly changing. They are exposed to sunlight, wind, and weather. But on these moons, the oceans are sealed beneath thick ice, isolated for eons. The ice acts as both a shield and a stabilizer. It blocks radiation from space and keeps the internal environment consistent, perhaps for billions of years. If life ever arose there, it could have had an unbroken stretch of time to evolve in peace. The icy moons are far colder than Earth, yet in some ways more stable for life. The same ice that freezes their surfaces preserves their oceans. The heat that keeps the water liquid doesn't come from sunlight, but from tidal forces, the constant stretching and squeezing caused by the gravity of their giant parent planets. That internal friction generates warmth, driving geological activity and potentially feeding hydrothermal systems on the ocean floors. NASA's approach to these moons has evolved from curiosity to active exploration. The Europa Clipper mission is well underway, set to arrive at the moon in 2030. It will perform dozens of flybys of Europa, mapping its surface, studying its magnetic field and using radar to peer beneath the ice. Its goal is to determine the depth, salinity and chemistry of Europa's ocean, and to look for hints of organic materials on the surface that may have been brought up from below. For the first time, NASA will be studying a potential ocean world up close, not just as a frozen sphere, but as a dynamic system. The agency's scientists also continue to analyze Cassini's treasure trove of data from Enceladus. Even though Cassini's mission ended in 2017, the samples it collected are still revealing secrets. Some researchers believe future missions could fly through the plumes again, equipped with more advanced instruments capable of detecting amino acids or even signs of metabolism. There are proposals for landers that could touch down near Enceladus's south pole and scoop up fresh material from the icy surface. NASA's challenge is balancing ambition with caution, designing missions that can confirm signs of life while avoiding contamination of these pristine environments. On Earth, ecosystems in the deep ocean survive entirely cut off from the surface, thriving on chemical energy alone. Could something similar exist in the dark oceans of Europa or Enceladus? Microbes clinging to mineral-rich vents, evolving in silence beneath miles of ice. As scientists study Europa and Enceladus, they are forced to reconsider the limits of life here at home. Microbes have been found thriving in glaciers, deep mines, and subglacial lakes, environments once thought sterile. These discoveries strengthen the case that life might adapt to similar conditions elsewhere. The line between Earth's extreme environments and extraterrestrial habitability is blurring. Even as NASA prepares its next steps, there's a quiet sense of awe surrounding these worlds. They are unlike anything humanity has explored. Alien oceans hidden beneath worlds of ice where no sunlight ever reaches, yet where energy and chemistry dance in the dark. Each of these moons holds a different version of the same ancient story, the meeting of rock, water, and heat, the ingredients that on Earth led to life. Titan, a laboratory of the weird. Titan is unlike any world humanity has encountered so far. While moons like Europa and Enceladus offer the promise of life as we know it, Titan offers something altogether different. This moon, Orbiting Saturn is a place where the surface is shrouded in a thick orange haze, where temperatures plunge to nearly negative 180 degrees Celsius, and where lakes and rivers are made not of water, but of liquid methane and ethane. With NASA's upcoming Dragonfly mission, Titan's strange atmosphere and surface will be explored in unprecedented detail, shedding light on whether life could thrive in a world so unlike our own. Titan's atmosphere is one of the thickest in the solar system, composed mostly of nitrogen, with traces of methane, hydrogen, and other organic compounds. The atmosphere is so dense that it acts like a thick fog, blocking much of the visible light from reaching the surface. Beneath that fog lies a world of extremes. Titan is a frozen moon, far colder than the coldest places on Earth. These temperatures are so low that methane and ethane, gases that are typically found in Earth's atmosphere in vapor form, exist as liquid lakes and rivers on Titan's surface. The presence of liquid methane and ethane on Titan immediately sets it apart from other bodies in the solar system. On Earth, life as we know it depends on liquid water, but Titan offers no liquid water. Instead, its lakes and seas are filled with hydrocarbons, carbon-based molecules that play a central role in chemistry but are typically associated with fuels and oils here on Earth. In Titan's thick atmosphere, chemical reactions occur in the cold, dark environment, leading to the formation of complex organic molecules that are precursors to more complex chemistry. These molecules could provide the building blocks for life, in a way that might be just as viable given the right conditions. The idea that life could exist in such a bizarre environment was once pure speculation, but Titan's potential as a laboratory for studying the chemistry of life has grown stronger with each new discovery. The Huygens probe, which landed on Titan in 2005, provided the first direct observations of Titan's surface. The probe found that Titan's surface was covered with a mix of icy materials and hydrocarbon lakes. Since then, NASA's Cassini spacecraft has continued to study Titan, mapping its surface, atmosphere, and weather systems, and helping scientists learn more about the Moon's strange and dynamic environment. But even with Cassini's groundbreaking discoveries, Titan remains largely unexplored. Scientists still don't know what the surface looks like in great detail, or how the methane lakes behave over time. How do the organic molecules in the atmosphere interact with one another, and what kinds of chemical processes are happening on Titan's surface? These are questions that NASA's upcoming Dragonfly mission hopes to answer. Dragonfly is a rotorcraft designed to fly through Titan's thick atmosphere, exploring its surface and taking samples of its lakes and soils. Unlike typical landers, Dragonfly will be able to travel from one site to another, sampling different regions of Titan's surface and studying how the chemistry changes across the Moon. The mission will focus on Titan's unique chemistry and weather systems, with the goal of understanding whether the Moon's organic molecules could support life and what form that life might take. One of Dragonfly's primary objectives is to study Titan's lakes. These liquid methane lakes could offer insight into how a different kind of life could survive in a solvent other than water. The hope is that Dragonfly will help scientists understand how organic molecules interact in Titan's frigid lakes and whether the conditions there could support life forms that might be completely alien to us. Scientists also hope that Dragonfly will help them understand Titan's weather patterns, which are driven by the evaporation and condensation of methane. Titan has its own kind of hydrological cycle, similar to Earth's water cycle. Methane evaporates from the surface, forms clouds, and then rains back down, filling the lakes and rivers. In fact, Titan's methane rain is likely to be one of Dragonfly's key areas of study. Just as Earth's water cycle creates rainstorms, clouds, and snow, Titan's methane cycle creates unique weather patterns, which could offer clues about how Titan's organic chemistry functions over time. One of the most exciting aspects of Dragonfly's mission is its ability to sample Titan's atmosphere and surface. The craft will carry instruments to analyze the chemical composition of Titan's surface materials as well as its air. Using its advanced tools, Dragonfly will be able to measure the abundance of organic compounds, map the distribution of methane and ethane, and study the chemical reactions taking place in the Moon's atmosphere. These analyses will allow scientists to better understand how complex organic molecules are produced on Titan and whether those molecules could be building blocks for life. Titan's extreme environment is a far cry from the familiar earthly conditions that we associate with life. Yet, the possibility that life could exist in such a different environment is one of the most exciting ideas in the search for life beyond Earth. And even if we never find life on Titan, the insights we gain from studying its atmosphere, surface, and weather systems could teach us more about the fundamental processes that govern the development of life, no matter how strange or different it may be. The search from orbit. For NASA, the search for life has always depended on orbiters, those quiet sentinels circling planets and moons, scanning the terrain below with unblinking eyes. These machines are the scouts of discovery, the ones that gather the clues which later guide where landers and rovers will go. They map the shape of a world, trace the flow of its ancient rivers, and detect the faint chemical fingerprints that might hint at habitability. When the Viking landers set down in the 1970s, they were guided by data from earlier orbiters that had photographed the planet's surface in detail for the first time. The images sent back by the Mariner missions revealed a world marked by canyons, craters, and what appeared to be dried river valleys. These images showed scientists that Mars had once been shaped by flowing water. But at that time, the instruments were limited, and much of the planet's surface remained a mystery. Over the decades that followed, NASA's orbiters grew far more powerful, equipped with advanced spectrometers, radar systems, and cameras capable of identifying minerals from hundreds of kilometers above the surface. One of the most influential of these orbiters has been the Mars Reconnaissance Orbiter, or MRO, which arrived at Mars in 2006. With its powerful cameras and sensors, MRO transformed how we see the red planet. It can capture details as small as a dinner table on the surface, revealing dunes, rock layers, and even the wheel tracks left by rovers. But MRO is more than just a camera. It's a geologist in orbit. Its instruments can detect minerals that form only in the presence of water, clays, sulfates, and carbonates that serve as chemical evidence of Mars's wetter past. By mapping where these minerals occur, scientists have been able to identify places that may have once hosted lakes or hydrothermal systems, areas where ancient microbial life could have thrived. Every rover mission that NASA sends to Mars relies on orbital data to choose its landing site. The Curiosity rover, for example, was sent to Gale Crater largely because orbiters detected clay minerals there, suggesting the presence of long-standing water. Years later, the Perseverance rover was directed to Jezero Crater for a similar reason. Orbital imagery had revealed a fossilized river delta, a place that once teemed with flowing water. Without orbiters to identify these features, such precise targeting would be impossible. Around Jupiter, NASA's Juno spacecraft continues to reveal new details about the planet's atmosphere and magnetosphere, offering hints about the conditions that shape its many moons. Around Saturn, Cassini's long orbit provided a wealth of data, not only about the planet's rings, but also about its moons. Even now, as NASA prepares for new missions to the icy moons of the outer solar system, orbiters are being designed to do what humans cannot yet do themselves: to explore vast and distant worlds from afar, gathering the evidence that will one day determine where to send landers. Remote sensing is, in many ways, the art of seeing the invisible. NASA's orbiters use different parts of the electromagnetic spectrum to peer beneath surfaces, through clouds and into chemical signatures. Cameras capture visible light, showing the colors and shapes of alien landscapes. Infrared sensors detect heat, helping scientists understand surface temperatures and compositions. Radar can penetrate ice and rock, revealing subsurface layers hidden from view. When these different data sources are combined, they create a three-dimensional understanding of a planet's geology and history, an understanding that can tell us where liquid water might once have existed or even where it might still be trapped underground. One example of this came when NASA's Mars Odyssey orbiter detected hydrogen in the Martian soil. Because hydrogen is a key component of water, this finding suggested that ice was hidden just below the surface. Later, the Mars Express orbiter, a collaboration between NASA and the European Space Agency, found more evidence of subsurface ice. These discoveries reshaped how scientists thought about Mars. Instead of being a completely dry desert, Mars appeared to hold vast reserves of frozen water, waiting to be explored. Such data also helped NASA choose where to send its next missions, toward the poles, where ice was more likely to be found. Orbiters have also played a vital role in monitoring planetary weather systems. On Mars, for instance, orbiters track dust storms that can grow to envelop the entire planet. These storms pose a risk to rovers on the ground, especially those powered by solar panels. By studying how these storms form and move, NASA can better protect its hardware and understand the dynamics of the Martian atmosphere. Remote sensing also allows scientists to study planetary evolution over time. By repeatedly imaging the same regions, NASA's orbiters can track changes, collapsing cliffs, new impact craters, shifting dunes. This not only reveals how active these worlds are, but also helps scientists identify regions of geological interest. The more dynamic a surface appears, the more likely it is to have processes that could support or preserve traces of life. Even when a mission's primary goal isn't to look for life, the data it collects can be repurposed for that purpose. For instance, NASA's Lunar Reconnaissance Orbiter, which was originally tasked with mapping the Moon's surface, has provided crucial information about the presence of water ice in permanently shadowed craters near the poles. Though the Moon is not considered a likely place for life, understanding where and how ice is stored there has broader implications. It shows how water can persist in extreme environments, offering a comparison point for similar processes that might occur on Mercury, Ceres, or other bodies. NASA's orbiters provide global context for local discoveries, helping scientists connect what a rover finds on the ground to what can be seen from above. When a rover like Perseverance finds an interesting rock layer or organic compound, orbiters can check whether similar features exist elsewhere on the planet. This partnership between orbiters and surface missions creates a continuous feedback loop, where discoveries on one level guide investigations on another. Orbiters also help manage the practical realities of space exploration. They act as communication relays, sending signals between rovers on the surface and mission control on Earth. This link is vital because direct communication from the ground to Earth is often impossible. Through these orbiters, data from rovers, images, samples, measurements are transmitted back to NASA scientists who can then plan the next day's activities. Without these orbital relays, the flow of information from distant worlds would be much slower and missions would operate with far less efficiency. As NASA continues to look beyond Mars, orbiters remain central to its strategy. Missions planned for Europa, Titan, and even distant asteroids will rely on remote sensing to find chemical traces of organic compounds, to locate ice beneath the surface, and to reveal the conditions that might allow life to take root. These eyes in the sky serve as our first and most enduring link to alien worlds. They teach us where to look, where to land, and where perhaps we might one day find something that looks back. The search on the ground. If NASA's orbiters are the eyes of exploration, then its rovers and landers are the hands. They are the ones that dig, touch, drill, and sample. They transform what we can only see from space into what we can actually measure and understand. It is where remote sensing meets physical contact, where abstract theories about habitability turn into real chemical evidence gathered from alien soil and rock. They are the closest thing we have to astronauts walking the surface of other worlds, their wheels leaving traces in the dust of planets that may once have known rivers, lakes, and perhaps even life. The Mars Pathfinder mission in 1997 was the first to carry a rover, a small-wheeled vehicle named Sojourner. It moved only a few meters per day, taking images and analyzing nearby rocks with a simple spectrometer. But even that small amount of mobility changed everything. For the first time, NASA could study multiple sites, compare rock types, and begin to understand Mars as a complex geological world. With the twin rovers Spirit and Opportunity, launched in 2003, NASA expanded that vision. These machines were far more capable, built to travel long distances and survive for months on the Martian surface. They carried cameras, drills, and instruments designed to identify minerals that form in water. Very quickly, both rovers found what NASA had been hoping for: evidence of ancient water. Spirit discovered volcanic rocks that had been altered by steam and heat, suggesting past hydrothermal activity. Opportunity rolled into an area filled with small spherical formations nicknamed blueberries, which turned out to be hematite, a mineral that forms in liquid water. But the real leap forward came with Curiosity. Unlike its predecessors, its tools were more like a mobile laboratory than a robotic explorer. Inside its body were instruments capable of heating samples to release gases, then analyzing those gases to detect carbon-based molecules. Its cameras could study fine layers in rock, revealing the slow history of sediment that once settled in an ancient lake bed. Its robotic arm could drill into rock, scoop up powder, and deliver it to the onboard lab for analysis. The rover discovered that Gale Crater had once hosted a long-lived lake, complete with all the necessary ingredients for life: carbon, nitrogen, sulfur, and phosphorus. It found clay minerals that could only form in neutral, non-acidic water. Later, it detected traces of organic molecules, the kind that could be left behind by biological processes or formed naturally through chemistry. Though it did not prove life ever existed, it made one thing clear: Mars had been habitable. The success of Curiosity paved the way for its more advanced successor, Perseverance. Rather than simply analyzing rocks on site, it would collect and seal samples for future return to Earth. Its goal was to find biosignatures. Perseverance carries a suite of instruments that allow it to investigate the Martian surface at a level of precision once thought impossible. Its Sherlock, or scanning habitable environments, with Raman and luminescence for organics and chemicals. Instrument uses a laser to identify complex organic compounds on rock surfaces. Another instrument, PIXL, or Planetary Instrument for X-ray Lithochemistry, can map the chemical makeup of rocks at microscopic scales. Together, they build a detailed picture of the planet's past environment. While orbiters provide the big picture, rovers explore the details. They can approach a rock, examine it from multiple angles, drill into it, and then move on to compare it with others. They can climb hills, cross dunes, and sometimes even revisit sites to take new measurements after months of weathering. But with mobility comes risk. Mars is an unforgiving place. Its thin atmosphere offers no protection from radiation, and temperatures can drop to -80 degrees Celsius at night. Dust storms can block sunlight for weeks, starving solar-powered rovers of energy. Mechanical failures too can end missions abruptly. Spirit, for instance, became trapped in soft sand and was unable to move. Yet despite these challenges, the persistence of these machines has been remarkable. Opportunity, which was expected to last 90 days, continued exploring for nearly 15 years. Curiosity, too, has been operational for over 13 years. Beyond Mars, NASA's experience with landers and rovers is expanding to new worlds. A future lander mission is being designed to touch down on Europa's frozen crust, drilling into the ice to search for organic material that may have been ejected from the ocean below. The technology for this mission draws on decades of rover and lander experience: how to collect samples, how to sterilize tools to avoid contamination, and how to analyze materials in environments far colder than Mars. Every rover carries the same underlying question that has driven NASA since Viking. If life ever existed elsewhere, how would we recognize it? These clues are subtle, and identifying them requires not only advanced instruments, but also context, an understanding of the geology and history of the site. Collecting and studying these samples on Earth will allow scientists to use even more sensitive tools, instruments too large or delicate to send into space. The rovers may move at the speed of a crawl, but through them, our understanding races ahead. they embody humanity's determination to touch the unknown, one-wheel rotation at a time. The limits of sterilization. Before a NASA spacecraft ever touches another world, before its instruments awaken under alien skies, there is a long and invisible battle that takes place on Earth, a battle against contamination. The spacecraft itself may be a marvel of engineering, built to survive radiation, cold, and the vacuum of space. But there's one thing it must not carry: us, or rather the microscopic forms of life that thrive all around and within us. A single fingerprint can hold millions of bacterial cells, and a single sneeze can send thousands of microscopic travelers onto a surface. For scientists hoping to find life beyond Earth, those same travelers could destroy everything. NASA calls it planetary protection, and it is one of the most delicate, meticulous, and philosophically charged practices in all of space exploration. The basic idea is simple. Don't contaminate other worlds with Earth life, and don't bring alien life, if it exists, back here without safeguards. But in practice, it is a constant struggle between biology and ambition. Every bolt, wire, and piece of metal that leaves this planet must be cleaned, baked, and tested to make sure it carries no unwanted passengers. The reason is not just scientific purity, it's also about responsibility. The fear is that if even a handful of hardy microbes from Earth were to hitch a ride and survive on another planet, they could either destroy native ecosystems or lead scientists to false conclusions about discovering life elsewhere. When the first missions to Mars were being planned in the 1960s, scientists realized that if they weren't careful, they might accidentally turn another planet into a biological mirror of Earth. A few microbes, carried unintentionally by a spacecraft, could grow, spread, and mix with whatever existed there. And if those microbes later showed up in an experiment designed to detect alien life, the results would be meaningless. To avoid that, NASA and other space agencies developed strict sterilization rules. Every mission that might touch a potentially habitable world had to be treated as though it were entering a fragile, untouched ecosystem. The Viking landers were the first spacecraft to undergo sterilization at an almost surgical level. After assembly, each lander was placed inside a giant oven and heated to over 110 degrees Celsius for several hours to kill any surviving microbes. Components had to be designed to survive the heat without warping or losing functionality. Even then, absolute sterility was nearly impossible to guarantee. The goal wasn't perfection, it was probability. NASA calculated how many microbial spores might remain and set limits that made the risk of contamination astronomically small. But as missions became more complex, the challenge grew. New instruments, more delicate materials, and intricate wiring made it harder to subject entire spacecraft to high temperatures. For modern missions like the Mars rovers, engineers had to find other ways to meet sterilization standards. Components are now cleaned with hydrogen peroxide vapor, alcohol wipes, and ultraviolet light. Some are built inside clean rooms where air is filtered, and technicians wear full-body suits. Every tool, every surface, every container is catalogued and tracked. Yet even with all of this, NASA knows that zero contamination is a dream. Earth life is tenacious. Extremophiles have taught scientists that life is far more resilient than once believed. Some bacteria form spores that can survive in space-like conditions for years, resistant to radiation and vacuum. A few can even live off minimal nutrients, subsisting on dust or trace gases. These discoveries have made the job of planetary protection officers far more difficult. If life can survive in such extreme environments on Earth, then perhaps some of it could also survive the journey to Mars or Europa. There is also the opposite concern: backward contamination. If a mission were ever to bring samples from Mars, Europa, or another potentially habitable world back to Earth, what precautions would be necessary to ensure nothing harmful was released? Scientists generally believe that the risk is very low. After all, if microbial life existed on Mars, it would likely be adapted to Martian conditions, not Earth's. Still, the protocols are designed for worst-case scenarios. Sample return missions involve sealed containers, multiple layers of isolation, and specialized handling facilities that resemble high-security biological labs. The goal is to protect Earth as carefully as we protect the other worlds. Should we even be trying to send our machines and potentially our microbes into pristine alien environments at all? This question divides even scientists. Some argue that planetary protection is a sacred duty, a form of cosmic conservation. They see other planets and moons as untouched laboratories of nature, perhaps holding forms of life that evolved completely independently of Earth. To contaminate them, even accidentally, would be to destroy something irreplaceable. Others see exploration itself as a natural extension of life's drive to expand. They argue that Earth life spreading to other worlds would not be contamination, it would be continuation. In their view, the spread of biology might even be a good thing, a way for life to seed the galaxy and survive long after Earth is gone. This debate becomes especially relevant as private companies like SpaceX plan human missions to Mars. Unlike NASA, these ventures are not bound by the same strict planetary protection rules. A single human mission would bring billions of microbes embedded in the astronauts' bodies, clothing, and habitats. Keeping Mars sterile under those circumstances is virtually impossible. The question then is whether the goal of keeping Mars clean can survive contact with human colonization. Some planetary scientists argue that we should intensify robotic exploration before humans arrive to ensure we can identify any indigenous life before it's overwhelmed. Others believe that if life does exist there, it has probably already adapted to Martian extremes and would not easily mix with ours. In recent years, NASA has begun re-evaluating its planetary protection standards. For worlds like the Moon or Mercury, where no liquid water exists, sterilization rules have been relaxed. But for Mars, Europa and Enceladus, places where life could exist, they remain strict. The next generation of missions, especially sample return missions, has forced NASA to rethink what clean really means. For example, Perseverance's sample tubes are sealed in ultra-pure environments. But even then, scientists know that a few microscopic particles from Earth might still be present. The challenge is to design analyses that can tell those apart from anything truly alien. Even the smallest error in sterilization can echo for decades. Imagine a future where scientists discover a strange microbe on Mars, only to realize it shares too much DNA with Earth organisms. Was it native or imported? Without absolute certainty, the discovery would forever be shadowed by doubt. That is the scenario planetary protection seeks to prevent. If life from Earth were to take root on another world, could that itself be seen as a kind of evolution? For billions of years, life has spread across this planet by accident, on winds, through ocean currents, carried by meteor impacts. Perhaps spreading into space is simply the next step in that long process. Some astrobiologists have even suggested that life might already be cosmic in nature, traveling from one world to another through natural impacts, a process known as panspermia. If that is true, then our efforts to prevent contamination might be standing against something the universe itself does naturally. Still, NASA's stance remains one of caution. Until we know for certain what other worlds hold, the duty is to protect them. Every spacecraft that leaves Earth carries an unspoken promise to explore without harm. That promise defines the ethics of modern space exploration. It is why engineers spend years designing systems to reduce contamination to the smallest possible level, and why planetary protection officers act as both guardians and skeptics, questioning every bolt, every seal, every touch. In the clean rooms of NASA's Jet Propulsion Laboratory, spacecraft are often assembled under bright lights and filtered air, surrounded by technicians in sterile suits. They look less like explorers being built, and more like surgical instruments being prepared for an operation. And in a sense, that's exactly what they are, tools designed to probe the body of the solar system without leaving scars. As the search for life grows more complex, the limits of sterilization will be tested again and again. Every future mission pushes closer to places where life might still exist. The challenge is not just to reach them, but to do so without losing our scientific innocence along the way. For all our technology and precision, we remain a biological species reaching into a biological universe. The smallest microbe may be the greatest traveler of all. Optical SETI and the new frontier of light. While most of the search for extraterrestrial intelligence has historically relied on radio waves, a new frontier in the quest to detect alien civilizations is opening up in the form of light-based communication, specifically optical SETI. Unlike radio signals, laser signals offer a new and potentially more efficient method of communication. These laser flashes, which can be focused and directed precisely, offer the possibility of detecting extraterrestrial technology with greater clarity and speed. This emerging field takes advantage of the same principles of light that we use in our own communications technology, but it pushes the limits of what we can detect in space. Laser light has the advantage of being much easier to distinguish from background noise than radio signals. The reason for this lies in the very nature of light compared to radio waves. Light waves are much shorter and more focused than radio waves, making it easier to direct and control them. While radio waves tend to spread out over vast distances, laser beams can be concentrated and directed in a specific way that allows for greater precision in communication. In essence, a laser signal could carry more information over long distances without being easily confused by other cosmic noise, such as the radiation from stars, galaxies, or other space phenomena. This makes it a potentially ideal way for advanced civilizations to send signals across the cosmos. NASA's telescopes and optical sensors, which are primarily used to study stars, galaxies, and other celestial bodies, can also be adapted to the task of looking for laser flashes that might indicate extraterrestrial intelligence. While radio SETI efforts rely heavily on large, sensitive radio telescopes that can detect the faintest signals from space, optical SETI requires specialized equipment designed to detect light flashes that are orders of magnitude more fleeting. This means that optical telescopes used for SETI must be extraordinarily sensitive, capable of detecting incredibly short bursts of light that last only a fraction of a second. NASA's existing optical telescopes, such as those used for exoplanet studies or star observation, could be repurposed for the search for alien laser signals. Telescopes like the Keck Observatory in Hawaii or Webb could theoretically be used to scan for bursts of light from distant stars. Optical SETI requires the ability to look at specific parts of the electromagnetic spectrum, particularly those wavelengths that are associated with laser emissions. For example, the wavelength of light emitted by a laser is very specific, and its pattern can stand out from the normal radiation emitted by stars, planets, or other cosmic objects. The narrowband nature of laser light makes it much more distinct than the broad range of radio waves typically emitted by natural sources. One of the primary challenges of optical SETI is that it requires extraordinarily precise detection methods. Unlike radio waves, which can be collected over a wide range of frequencies, optical signals need to be captured and analyzed with pinpoint accuracy. This means that scientists must know exactly what kind of light to look for, and they must have telescopes and sensors that are capable of detecting faint flashes of light. While radio telescopes have long been a reliable tool for SETI researchers, optical SETI requires a different kind of precision. Another challenge for optical SETI is the problem of distance. Although laser signals may be more focused and detectable than radio waves, the vast distances that separate us from other stars make it more difficult to detect these signals. A laser beam from an alien civilization could be directed toward Earth from a star thousands of light years away. While the beam may start out focused and powerful, by the time it reaches Earth, it may have spread out and weakened significantly. Even the most powerful lasers might be indistinguishable from the natural background noise of space by the time they reach Earth. Despite this, the focused nature of laser light means that if a signal were detected, it would likely stand out as a distinct burst, unlike the broader and more diffuse radio signals that make it difficult to pinpoint the origin of extraterrestrial signals. The potential advantages of optical SETI are clear. Additionally, optical signals, by their very nature, may be far more intentional. Laser flashes are difficult to produce naturally, so it is reasonable to assume that if we detect them, they may be intentionally directed toward Earth. This makes optical SETI potentially more straightforward than radio SETI, where natural sources can often produce radio signals that resemble the kind of signals researchers are searching for. New technologies and techniques are rapidly being developed to make optical SETI more practical and efficient. For example, the use of photodetectors, which are capable of measuring light with extreme sensitivity, is becoming more advanced. These detectors can measure even the faintest flashes of light and can be tuned to detect specific wavelengths associated with laser emissions. This means that the tools needed to detect optical signals are becoming more powerful and more finely tuned, which increases the likelihood of finding a signal that would otherwise have been missed. One of the most promising developments in optical SETI comes from the use of so-called optical SETI surveys, which are surveys that systematically search for laser signals across different regions of the sky. These surveys use sensitive optical telescopes, which monitor large areas of the sky for transient light bursts that could potentially indicate an artificial signal. Because light-based communication is so much faster than radio, these surveys can detect signals much more efficiently, covering large regions of space in a shorter amount of time. These surveys often focus on nearby stars, where the chances of detecting a signal are higher, but they also look to the far reaches of the galaxy to search for any signs of alien intelligence. While the vast distances and the challenges of detecting such faint signals may make optical SETI a daunting task, the potential rewards are immense. Laser flashes, with their focused nature and distinct signatures, could provide the breakthrough that SETI has been waiting for. As our tools and technology continue to advance, it may not be long before we start listening to the universe in a whole new way. Other eyes on the sky: ESA, Roscosmos, CNSA, and beyond. NASA may be the most well-known space agency in the world, but it is far from the only one. Over the past several decades, space agencies from Europe, Russia, China, Japan, and India have made substantial contributions to the quest for extraterrestrial life. Each brings unique perspectives, resources, and cultural approaches to the challenge, shaping the search in ways that complement and expand the efforts of NASA. Together, these agencies have created a global network of scientific exploration that transcends national borders. The European Space Agency, or ESA, has long been a key player in astrobiology research, and its approach to space exploration is deeply informed by Europe's scientific traditions and collaborative spirit. ESA's involvement in the search for life began with its early missions to Mars, such as the Mars Express orbiter, but ESA's most significant contribution to astrobiology came with the ExoMars program, a joint effort with Russia's Roscosmos. ESA's approach to astrobiology emphasizes international collaboration. Rather than acting alone, ESA often works in partnership with NASA, Roscosmos, and other space agencies to maximize resources and expertise. This collaborative approach is rooted in Europe's broader cultural ethos of scientific cooperation. European scientists have a long history of working together across borders to tackle complex challenges, and this spirit is reflected in ESA's missions. ExoMars, for instance, combined Russian expertise in lander technology with ESA's proficiency in scientific instruments. Russia, through Roscosmos, has also played a pivotal role in the search for extraterrestrial life. While the country's focus has historically been on human spaceflight, Russia has made important contributions to robotic missions aimed at exploring planets and moons in our solar system. Russia's space program has been instrumental in the study of Venus, launching missions such as Venera that returned valuable data about the planet's atmosphere and surface. Although Roscosmos does not have a dedicated astrobiology program like NASA or ESA, the agency's contributions to planetary exploration have provided valuable insights into the potential for life in extreme environments. China's space agency, the China National Space Administration, or CNSA, has rapidly advanced its space exploration efforts over the past 2 decades. While China's primary focus has been on developing its human spaceflight program, CNSA has also turned its attention to planetary exploration and astrobiology. In 2021, CNSA launched the Tianwen-1 mission to Mars, which included an orbiter, lander and rover, Zhurong. This mission marked China's first successful landing on Mars and the country's entry into the global race to explore the Red Planet. Zhurong's primary goal is to search for signs of ancient water and potential microbial life on Mars, aligning with broader global efforts to understand the planet's habitability. While China is still in the early stages of its astrobiology research, its growing investment in planetary exploration, combined with its highly capable space technology, ensures that the country will play an increasingly important role in the search for life beyond Earth. Japan's space agency, JAXA, has been a quiet yet influential contributor to the study of astrobiology. Japan's space program has focused on both robotic missions and scientific instruments that contribute to the broader understanding of astrobiology. JAXA's Hayabusa 2 mission, which successfully returned samples from the asteroid Ryugu in 2020, has provided insights into the building blocks of life, such as amino acids and other organic compounds. The discovery of these compounds on an asteroid, where conditions are thought to closely resemble those of the early solar system, has important implications for understanding the origins of life on Earth and the possibility of life elsewhere in the cosmos. Hayabusa 2's mission is part of a larger effort by JAXA to study organic chemistry in space and its potential role in the development of life. JAXA has also participated in international collaborations, including its partnership with NASA in the construction of the James Webb Space Telescope. India, through the Indian Space Research Organisation, or ISRO, has emerged as a significant player in the field of space exploration, albeit on a smaller scale compared to NASA or ESA. India's space program has made major strides in recent years, with missions like the Mars Orbiter mission, Mangalyaan, in 2013, which made India the first Asian country to reach Mars orbit. Although Mangalyaan's primary mission was to study the Martian atmosphere and surface, it also laid the groundwork for India's future involvement in astrobiology research. ISRO has continued to expand its capabilities, and its Chandrayaan-3 lunar lander made India the fourth country to ever land on the Moon. India's contributions to the search for life may not be as high profile as those of other space agencies, but its low-cost, high-impact approach to space exploration has made it an important partner in global efforts to explore the universe. In addition to these national agencies, numerous private entities around the world are also contributing to the search for life in space. Companies like SpaceX, Blue Origin and Rocket Lab are driving innovation in space exploration, providing new technologies and capabilities for planetary exploration. While private companies have typically focused on space transportation and infrastructure, their efforts are gradually shifting towards scientific goals, including the search for signs of life. SpaceX, for example, has proposed launching missions to Mars in the near future, while companies like Blue Origin are developing technologies for space tourism and lunar exploration that could eventually aid in the search for life on the Moon and beyond. As the search for extraterrestrial life continues, the contributions of these various agencies and companies highlight a crucial point. The quest to answer the question of whether we are alone in the universe is a global effort. Each spacefaring nation brings its own strengths and resources to the table, and the results are greater than the sum of their parts. The diversity of approaches also offers unique advantages. For example, Europe's emphasis on international collaboration, coupled with Russia's historical expertise in planetary exploration, complements the innovation and boldness of China's space program. Japan's contributions to organic chemistry and astrobiology, along with India's growing role in planetary exploration, further enrich the global effort. Together, these efforts paint a more comprehensive picture of the search for life in the universe, allowing scientists to combine their expertise and knowledge to tackle one of humanity's greatest challenges. While the scientific approaches may differ, the underlying motivation is the same: a desire to understand the universe and our place within it. Whether it's NASA's rovers on Mars, ESA's missions to Venus, China's exploration of the Moon, or Japan's study of organic compounds in asteroids, each of these contributions is a step toward answering the question that has long captivated humanity. Artificial life as a test case. In the search for life beyond Earth, NASA scientists are also exploring the possibility of artificial or synthetic life, both in the form of computer programs and synthetic cells. This approach, which may seem strange at first, is helping researchers rethink what life might actually look like elsewhere in the universe. By studying artificial life, scientists are challenging old assumptions and developing new ways to refine their search criteria. One of the key goals in this area of research is to simulate the processes that drive life, such as evolution and metabolism, in laboratory settings. By doing so, scientists can learn more about how life might emerge and sustain itself in environments that are very different from Earth. A significant part of this research involves digital life, which refers to computer programs that simulate the processes of biological life. In these simulations, scientists create models of evolution and natural selection, allowing them to explore how life might evolve in digital environments. These models are often referred to as artificial life or a life, and they allow scientists to simulate the growth, reproduction, and adaptation of life forms without needing to rely on biology. These digital organisms can evolve over time, with the ability to adapt to changing conditions, replicate themselves, and even mutate to create new forms of life. By studying artificial life, scientists gain insights into how biological life might evolve in environments that are far from Earth-like. For example, by simulating life in extreme conditions, such as in the high radiation environments of distant planets, researchers can begin to understand what kinds of adaptations would be required for life to thrive in these harsh settings. Another exciting aspect of artificial life research is the creation of synthetic cells. These are laboratory-created cells that mimic the basic functions of living organisms. Researchers have been working on creating synthetic cells that can carry out processes like metabolism, energy production, and even self-replication. These synthetic life forms are not quite the same as the life we know, but they provide a model for understanding how life might emerge from non-living matter. By studying synthetic cells, scientists can better understand how simple molecules might come together to form complex, self-sustaining systems. One of the most important experiments in this field has been the creation of synthetic protocells. These are simple, membrane-bound structures that mimic the basic features of living cells. While they don't have the full range of functions that living organisms possess, they are capable of basic metabolic processes and can even replicate themselves under certain conditions. These protocells are important because they help researchers understand the very basics of life, how molecules can come together to form structures that are capable of self-replication and metabolism. Simulating evolution through artificial life also helps scientists think about the broader question of whether life is a universal phenomenon. By running these simulations, scientists can see how simple programs or synthetic cells evolve over time, given certain environmental pressures or challenges. They can observe how these digital or synthetic life forms adapt to their surroundings, mutate in response to changes, and eventually become more complex. By understanding the patterns of evolution in artificial life forms, researchers can refine their criteria for what constitutes a viable environment for life to emerge. This could guide missions to distant planets, as scientists know what kinds of evolutionary patterns might be most likely to arise in specific environmental conditions. Perhaps one of the most interesting aspects of artificial life research is the role of lifelike systems that are entirely computer-based. These systems don't use any biological components at all, but they mimic the processes of living organisms in a digital environment. Digital life is an evolving field where researchers build computational systems that operate similarly to living organisms. These systems can evolve over time, just like real-life organisms, and can even develop strategies to adapt to changes in their virtual environment. While these systems are clearly not biological, they provide valuable insights into the mechanics of evolution, replication, and adaptation. As more space missions search for signs of life, it is essential that scientists are able to distinguish between biological and non-biological processes. While some planetary conditions may allow for the formation of life, others might create chemical reactions that mimic life but are not actually biological in nature. By studying artificial life, scientists can gain insight into how these false positives might occur and develop methods to avoid misinterpretation of data. While synthetic cells and digital organisms may never replace traditional life forms, they are helping scientists refine their understanding of what life could be and how it might function in diverse environments. As we continue to explore the universe, these insights will play a key role in ensuring that NASA's search for extraterrestrial life is as comprehensive and accurate as possible. The challenge of alien minds. The limitations of human cognition and perception create a unique barrier when it comes to recognizing alien minds. For instance, our brains are wired to recognize patterns based on the information we've received throughout our lives, information that is shaped by the earthbound environment we have evolved in. Our sense of space, time, and logic is based on our physical experiences. We think in terms of cause and effect, of events happening in a linear fashion, and of the world existing in 3 dimensions. Our understanding of intelligence, too, is heavily influenced by what we know from life on Earth. For instance, when we search for intelligent life in the universe, we often look for signs that might resemble human thought or behavior. This could mean searching for radio signals, mathematical patterns, or structured communications that resemble the way humans organize knowledge or share ideas. But what if extraterrestrial intelligence doesn't operate within these familiar frameworks? What if alien minds perceive time differently or communicate in ways that don't involve sound or light at all? What if their intelligence is based on a completely different set of principles, one that may be unfathomable to our limited understanding? In this context, the challenge of finding and interpreting alien intelligence becomes far more complex than just identifying a signal or a message. It requires us to confront our own biases and assumptions about what intelligence is and how it might manifest in forms radically different from our own. Our brains are products of millions of years of evolution, shaped by the specific needs of survival on Earth. We have developed an understanding of the world through our senses: sight, sound, touch, smell, and taste. And this has influenced the way we think and reason. In addition, our sense of intelligence is largely based on the intellectual capacity to solve problems, manipulate the environment, and communicate with others. This framework has worked well for us, but it may not be universal. If an alien civilization uses a completely different form of communication, one that doesn't rely on electromagnetic signals, it might be entirely beyond our ability to detect it. What if alien thought processes are based on entirely different sensory modalities, perhaps on chemical or vibrational signals that we can't even perceive? We know that life on Earth uses a vast array of methods for communication, from the complex language of dolphins to the chemical signaling of ants or bacteria. But these forms of communication are still grounded in biological principles that we understand. What if an alien civilization uses a form of communication that is so far removed from our own understanding of language that we would simply be unable to recognize it, even if it was happening right under our noses? In addition to sensory differences, there is also the question of cognitive differences. Human intelligence, for all its sophistication, is still based on certain assumptions about how the world works. We approach problems with logic, reason, and patterns that make sense within the context of our own existence. But what if an alien civilization thinks in ways that don't rely on logic as we understand it? What if their thought processes are based on entirely different principles, perhaps involving multidimensional thinking or forms of non-linear reasoning? Our ability to comprehend or interpret their methods of thought could be severely limited by the very nature of how our minds work. This leads to a broader question. What is intelligence and how do we recognize it? In earthbound biology, intelligence is often defined by certain traits: problem-solving ability, learning, communication, and self-awareness, to name a few. But could intelligence take on a form that doesn't align with these definitions? Could a super-intelligent alien civilization operate in a way that transcends our understanding of knowledge or reasoning? In a way, this opens up the very question of whether our concept of intelligence is too narrow or too Earth-centric to be applicable across the galaxy. Could an alien civilization be so advanced that we would fail to recognize it because its intellectual framework is simply too different from ours? Human beings have a tendency to project their own experiences onto the unknown. When we imagine extraterrestrial civilizations, we often picture them in terms that are familiar to us. Movies, books, and media portray aliens in ways that are comfortable for us, either as creatures that look vaguely human or as beings with motivations and behaviors that align with our own. We tend to assume that if an alien civilization exists, it will follow some form of logic or pattern that we can understand, or that it will communicate with us in a way that fits within our known methods of interaction. However, this assumption may be flawed. Just as humans have developed a wide variety of cultures, languages, and ways of thinking, it is likely that alien civilizations would be influenced by their own evolutionary paths and environmental conditions. Their cognitive frameworks might be shaped by entirely different challenges than the ones we face, and they might have developed a different understanding of what it means to be intelligent. Just as we don't fully understand the complexity of animal cognition on Earth, consider the intelligence of dolphins, elephants, or cephalopods. How could we expect to fully grasp the cognitive processes of beings that evolved under entirely different conditions? If we do make contact with an alien civilization, how would we even begin to understand their form of communication? On Earth, we often rely on shared languages, symbols, and behaviors to communicate. But if an alien species communicates in a manner that is completely outside the realm of human understanding, such as through patterns of color changes, electromagnetic pulses, or quantum entanglement, how would we decode the message? The process of understanding alien communication would be like trying to decipher a new language, but one with no common linguistic or cultural ground. The discovery of extraterrestrial intelligence would undoubtedly be one of the greatest achievements in human history, but it would also require us to stretch our minds to the limits of what we can imagine. We may find ourselves grappling with questions that have no easy answers. What would an alien civilization want from us? Would they even want to communicate with us? And if they did, how would we respond? Human beings have a long history of anthropocentrism, the belief that humans are the central or most important species in the universe. This belief shapes how we approach the concept of alien intelligence. If we discover an alien civilization, we may initially interpret its actions, motivations, and behavior through a human-centric lens. We might assume that they share our desires for communication, or that they follow the same basic principles of logic and reason that guide us. However, this assumption could be as limiting as it is dangerous. Alien intelligence, if it exists, may have motivations, behaviors, and desires that are completely alien to us, and we may never fully understand them. Recognizing alien intelligence, then, requires not only advanced technology and keen scientific insight, but also an open mind, one that is willing to entertain the possibility that intelligence may manifest in ways that are beyond our comprehension. It may be that the true challenge of discovering alien intelligence is not just in finding it, but in learning to recognize it in all its strange, mysterious forms. When communication becomes impossible, the idea of exchanging ideas, culture, or knowledge with intelligent beings from distant stars is a captivating one. Yet, as much as the concept of first contact stirs our imagination, the reality of two-way communication with an extraterrestrial civilization presents daunting, almost insurmountable challenges. These challenges are not just technological, they are also deeply rooted in the practical limitations of space, time, and cognition. First, Consider the issue of distance. The vastness of space is both awe-inspiring and daunting, and it is the single most significant obstacle to meaningful communication with alien civilizations. Even if we detect a signal from a civilization thousands of light years away, the time it takes for that signal to reach us and for our response to return renders any real-time conversation utterly impossible. Light, the fastest thing in the universe, takes time to travel across the expanse of space, and even at its incredible speed, it faces an inevitable delay when sent across vast distances. For example, a signal traveling to Proxima Centauri, the nearest known star system to our own, would take just over 4 years to reach Earth. If that civilization were to respond to our signal, it would take another 4 years for us to receive their reply. This is the simplest scenario, assuming the signal is sent in a straightforward, direct manner, without the interference of cosmic phenomena. Now imagine that the civilization we are attempting to communicate with exists much farther away, say, in a distant galaxy millions of light years from Earth. The delay would be mind-boggling. What is the point of engaging in a conversation when each response takes millions of years to return? The practical reality of time lags makes the kind of back-and-forth dialogue we might envision in the movies extremely unlikely. By the time a response from an alien civilization reaches us, we might no longer exist. Given these enormous delays, the question arises, is two-way communication even possible? On a human scale, two-way conversations are often essential for understanding and building relationships. They allow for the exchange of ideas, correction of misunderstandings, and deeper engagement. But when faced with the vast distances of space, the sheer delay in communication would render this kind of dynamic interaction almost impossible. The realities of these long delays suggest that the best outcome we might hope for is not a full-fledged conversation, but the detection of proof that an alien intelligence exists. This brings us to a second issue: signal degradation over vast distances. As signals travel through space, they are subject to various types of interference. Cosmic radiation, dust, and even the curvature of space itself can cause signals to weaken, distort, or become garbled by the time they reach us. Even with the most powerful telescopes and the most sophisticated equipment, a faint signal sent from an alien civilization millions of light years away could lose so much of its strength and clarity that it would be difficult, if not impossible, to decode it. In this context, receiving a clear signal from an alien civilization is in itself a remarkable achievement, even if the message is incomplete or distorted. However, interpreting that message is a completely different challenge. We might receive a signal, but understanding it may be beyond our reach due to the vast differences in technology, language, or the nature of the communication. The question of incompatible cognition is yet another hurdle. As we have discussed earlier, the nature of alien intelligence is something that we may not be able to understand in its full complexity. Even if they send us a signal that contains information, the way in which that information is encoded might be completely alien to our understanding. If an alien intelligence does not communicate in ways that we recognize, then communication may become an exercise in futility, no matter how much time or energy we devote to decoding it. What if alien civilizations exist in ways that do not prioritize communication, or that do not even consider the possibility of contacting other civilizations? The sheer diversity of life on Earth, from the simplest bacteria to the most complex primates, demonstrates that intelligence can take many forms. It is entirely possible that extraterrestrial intelligence might not be interested in engaging with us, or that their methods of communication could be so different that we would never recognize them as intentional at all. Even if an alien civilization is capable of communication, it might not have any interest in communicating with us. The motivations behind such communication are entirely unknown. The age-old question of whether they would even want to talk to us remains one of the central uncertainties in the search for extraterrestrial life. Would an advanced civilization have any reason to engage with a relatively primitive species like humans? Or would they simply view us as too insignificant to warrant attention, just as we might regard an ant colony as interesting, but not worth our effort to engage. These practical and philosophical limitations suggest that the best we can realistically hope for in the search for extraterrestrial intelligence is proof of its existence, not direct communication. This could come in the form of a signal that is so clearly artificial that it can only be interpreted as evidence of intelligent life. Alternatively, it could come through the discovery of artifacts, beacons, or other remnants left behind by an advanced civilization. The existence of such a civilization might become clear to us, even if we cannot ever directly communicate with it. The recognition of their existence, even without direct contact, would still fundamentally alter our place in the cosmos and reshape our understanding of life. Will NASA discover signs of alien life during our lifetimes? Leave your thoughts in the comments, and if you enjoyed this voyage, consider leaving a like and subscribing to the channel. Thanks for watching.